All right. So we want to look at multilinear. So we looked at the univariate polynomials already, and now it's time to look at more than one variable. Univariate polynomials have just one variable. So now we're looking at polynomials that have more than one variable, but we're looking at a very special kind of multivariate polynomial. Look at multilinear polynomials. So multilinear polynomials are polynomials that every variable has maximum degree of 1, right? So you're not going to have any variable that has like square or cube raised to the power 4, any n number. The maximum you can see is 1. Does that make sense? So the reason why we use this is like, we're going to be looking at sum check and we're going to be looking at GKR, and all those protocols make use of multilinear polynomials. They do that because of multilinear polynomials have very low degree so like polynomials hold data, right? And multilinear polynomials allow you to hold more data with less degree. I don't know if that makes sense. So when we look at Schwarzschild lemma, we'll understand why the degree matters, right? So once we understand why the degree matters, we'll now understand why they use multilinear a lot. But for now, we'll just focus on multilinear polynomials. Woo. Is it upper charge? Oh. This one is 4%, that's why.
Thank you, Daddy. Why is it not on?
There's a screen for
When I on our money, it doesn't.
I complain.
Alright, yeah. So it was just asking like if we can show you graphical representation also. So the thing now is like we said, multilinear polynomials are using more than one variable now, right? Which means that it will be more than the dimension increases, right? So a flat graph is 2D, which means x, y, right? So just two variables. Y is the output. X is just the. So if you want 3D, you have a polynomial that has two inputs, right? Let's say x, y, then the output is z, right? That's a 3D structure. That's the best that we can visualize because we live in a 3D world. But then if you start going up, let's say 4D, so you have a multilinear polynomial or any multivariate polynomial that has 3 variables and 1 output. That's a 4D structure. You can't visualize that. We as humans, at least, we can't visualize that because we don't work in that 4D space. You can't visualize it fully, but there's a way to slice a 4D structure. So you know how you have like a 3D structure, and that 3D structure you can look at it from one face, right? And then you see like a flat. So let's say you have a cube. You're holding a cube. If you look at it from this side, you might see a flat 2D surface, right? And you look at it from this other side, you might see another 2D surface. So like my iPad now, right? This is a 3D object. If I look at it from this side, all I see is this. You get? So this is a 2D projection of this 3D object. So I'm projecting a 3D object onto 2D space. Does that make sense? Yeah. If I look at the top, I'll just see this flat surface. So you can imagine I'm a 2D creature. Like I don't see in 3D. I see only in 2D. So this iPad now, I can never see it fully. I can only see projections of the iPad. So I'll just be looking at this, and the only thing I'll see is this. I have no idea that there's something else here. You understand? So it's actually the same thing for 4D. So 4D, you can imagine there's a creature somewhere, maybe like another alien species or something, that their native D dimension is 4. So they will be seeing structures that we just can't see. We just cannot see it. So we can see projections of it. So the same way like this 3D object, if I look at it from one side, I see a 2D object. That 4D object, if I look at it from a side, I'm going to see a 3D object. So it's really trippy. It's like the faces of that object are other 3D objects. But then there's this like really big 4D object. So there's you have a point, you have a line, that's 1D. You have a square, that's 2D. You have a cube, that's 3D. There's now something called a tesseract, which is like 4D following that cube trajectory. We are going to be working in crazy dimensions. You don't need to visualize it all, but the way things work in, let's say, 1D or 2D or 3D is exactly the same way it works in all the dimensions. So when we're explaining the nature of these structures, we'll most likely just use 3D, 2D. But then the ideas or the insights that you get, we apply in all the dimensions. You get? So let's start. Yeah? Visualize it. Why do we need to work with crazy dimensions, or why do we care about visualizing it? So what we're doing now is like, we are using structures to hold information. So we are storing data on these structures. So you have already learned how to store data on like lines, right? 2D lines. That's univariate polynomial. So now there are other structures that can still store data. So multilinear polynomials are an example of one. Now, you need space to store data. If your structure doesn't have space, it can't store data. So if you want to store like 50 numbers, you know that you need a degree 49 polynomial, right? So it's something similar. You can use a square to store just 4 points, for example. But you can use a cube to store how many points? Or mathematicians, 1, 2, 3, 4, 5, 6, 7, 8, right? I'm just looking at the at the corners, exactly. So you can use a tesseract to store way more. So the reason why we're working with crazy dimensions is because of we're just going to be storing like a lot of points. You get? But the visualization is to help us discover like a really, really efficient algorithm, right? So we'll do coefficient form first, and then we'll talk about another form. The other form we'll derive it, we'll rediscover it. Because me and Francis, there was no tutorial per se that we just like looked at the math of it, and then we reverse engineered it. And then we now realized that, oh, this is what... So Aquox has an implementation of what we're going to talk about. And by reverse engineering, we now figured out how exactly like they were able to get what they got. So you guys to try and reverse engineer it too. And
So do you have Francis together?
we learn together, yes. Alright. I don't know where to start from. I won't lie. I won't lie, yo. Okay. Francis, I'll send you meat. So we'll do coefficient form for multilinear. Then we'll teach like Lagrange. You guys will try and derive Lagrange yourself actually. We'll see if you guys can come up with it. It's very similar to the other one. But it's fun, it's fun, it's really fun. It's fun, it's fun. Francis, the last one I sent. Use the last one I sent on TG. I'm just doing backup recording in case it's the other one messes up. Okay, let's begin. Okay, so multilinear polynomials, no variable has more than one power, alright? So an example is this: f of x comma y is equal to, let's say, like 2x plus y, for example, right? X degree 1, y degree 1. Is it power, like exponents, right? I won't say degree. Degree is more like polynomial. So what is the degree of this polynomial? Okay. What is the degree? And is it multilinear? Why is it not multilinear? What is the power? Okay, it's my handwriting. No, it's my handwriting.
No, it's not power, it's
I'm coming. Sorry, it's my handwriting. It's my handwriting. This is y. So what is the degree? 2, right? So do you know how we got that? For the people that were not around, each of these are monomials, right? So the degree of a polynomial is the highest degree of the monomials. So you check the degree of each monomial, and the highest one is going to be the degree of the polynomial. And the degree of a monomial is the sum of all the powers of all the variables. So like monomials are the things between plus. So this has two monomials, 2xy and 3yz. Okay? So to find the degree of 2xy, look at the powers of x and y, and you add them up. So the degree of the first monomial is 2. X has power 1. Y also has power 1. So 1 plus 1 is 2. So the degree of that one is 2. What's the degree of the other one? 2 also. So what's the highest one? Still 2. So the degree of the entire polynomial is 2. You get? So this one is just for her now. That's Z. I'll use P. What's the degree of this? Wait, hey, I did not. What's that again? It's for her. The highest monomial. 11. I don't know. I've not calculated. 3 plus 2, that's 5 plus 4, 9, 10, 11. Then there's the other one is 3. Then the highest one is 11. So the degree of this polynomial is 11. Then it's a multilinear multivariate. Why is it multivariate? Because it has variables that have power more than 1. Right, that one has 3 too. So this is multivariate. Why the other ones are multilinear? So today we're focusing on multilinear because future protocols are using multilinear. Makes sense so far? Yeah. So the way we will use multilinear most of the time is that we are given the data, right? So we're not going to be given the polynomials directly. The same like in invariants, we could just say 2x squared plus something. we are given the data that we want to store. Then most of the time we're supposed to find the multilinear polynomial that can store this information. Does that make sense? So what I'm saying now is that we're given the points of the polynomial. Then we're supposed to interpolate to find the polynomial itself. So there's an equivalent Lagrange interpolation for multilinear polynomials. Okay? Does that make sense? Now, this polynomial, the interpolating set is different. Remember, the interpolating set for the other one could have been any x value, right? 0, 1, 2, 3, blah, blah, blah. Now, because we have more variables, it's not just a single number. Okay? So like this one now is f of xy. You can't just use 0, 1, 2, because we have two variables here. And in order to keep it multilinear, we have to restrict our interpolating set to zeros and ones. Okay? We have to restrict it to, I don't think it depends. But we walk over something called the Boolean hypercube. I'm going to give, so I'll give the high level description of the Boolean hypercube now. Then when we start looking at these things graphically, we'll now start looking at the graphical intuition for how it works. So the high level representation is that the Boolean hypercube is basically just all possible combinations of zeros and ones in that variable number. So like this one now we have just two variables. So that means that we'll have 0, 0, 0, 1, 1, 0, 1, 1. All possible combinations of zeros and ones. So this is the Boolean hypercube of length 2. When I say length, I'm talking about the bits length. Okay? So what if we had just f of x? What's the Boolean hypercube for this? Just 0 and 1. Right? That's all possible. Okay? Then we had this. So do you know how you would do the enumeration? Yes. So there's an easier way to do it actually. No, I won't say easier. If you don't know how to do it that way, what you could do is you could go from, so like this 0, 1 now represents a straight line. So imagine a straight line like this. This is f of x. This here is 0. This here is 1. Now this one here represents a square. Okay? So it's something like this. So a way to construct this square is to start with a straight line. You duplicate it. Right? And then one half will take 0 prefix. The other half will take 1 prefix. Does that make sense? So this will be 0, 0. So I'm going to put 0 in front of this. And then I'm going to put 1 in front of this. So this just automatically generates this for us by just reading 0, 0, 0, 1, 1, 0, 1, 1. Does that make sense? Then likewise, you can do the same. Now you're going from a square to a cube. So you just copy the entire thing. Right? So one of the squares is going to have 0 prefix everywhere, while the other one is going to have 1 prefix everywhere. Okay? So you now have 0, 0, 0, 0, 0, 0, 0, 0, right? So this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. While the other one will have 1s everywhere. So 1, 1, 1, 1. So if you now read it out, you'll be able to get like the Boolean hypercube. But there's a way to do it without drawing all these like diagrams, right? So you start with just 0, 1. This is like your square. So if you want to go to the next dimension, you just add, you duplicate it, you rewrite what you have written, and then you put 0, 0 for the first half and 1, 1 for the second half. So this is 0, 0, then 1, 1. Now if we want to get to the next one, we copy the entire thing again. So this will be 0, 0, 0, 1, 1, 0, 1, 1. Then the first half will add zeros. So 0, 0, 0, 0. Then this one is 1, 1, 1, 1. You get? And all these are basically like there's another way to do it, right? Like they're numbers. So this is 0 in decimal. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7. So this is just the decimal representation of binary representation of the following decimals. Does that make sense?
I saw the way you do that computing. Can we do it for the next stage?
From what?
For the next.
Wait.
Do you want to do that computing?
Wait. Are you talking about the cube?
Yeah.
I should copy the cube.
Copy the cube too and do it for the next.
I should go to 4D. Okay. No.
Actually, there's a formula
For what?
for generating it.
What do you mean?
The formula to make rather than thinking of drawing of whatever. Okay, you can x, y,
Uh-huh.
that is like what we are going to get is 4. That is 2 raised to power. It's just like power.
Yes.
2 raised to power 4.
Then you enumerate,
You know
right?
that for that 4 is what 0, 1, 2, 3.
Yes.
So you convert 0, 1, 2, 3
So decimal. Yeah.
So when 3D is 2 raised to power 8.
Yeah.
You get from 0 to 7.
Mm-hmm.
Convert it to decimal.
Yeah.
When,
So that's why I said the mapping exists. So that will now be like when we're implementing, we will now. So that's a 4D shape.
Yes. Can we copy?
We should draw a 4D shape. We can technically do it, right? I don't know how to connect it. I don't know how to connect it. But I'll just add the distance first. I'll add zeros here first. Right? And then the other one I'll add ones. But I don't know what this shape is. This is supposed to be the tesseract side. But then you're supposed to now like You said I should. I don't know what this is. I don't know what this is. But it's very correct, yeah.
If you can see spiritual things, you need to see.
Kind of like
So I'll just talk about the Boolean hypercube, right? And I'm showing like different ways that you can. So what Israel was saying was so there's a way to know how many elements are representable directly, right? You know this one now can only represent 2 values, right? One at this side, one at this side. Then a square can represent 4 values. One here, one here, one here, one here. So you do 2 to the number of variables. So the number of variables here is just 1, right? This is f of x. Right number of variables here is 2. F of xy. You get? And the number of variables on this is 3. F of x, y, z. So the number of elements each can represent is just 2 to the number of variables, right? Yeah. So the first one, 2 to 1, is 2, right? So that's why this can represent 2 values. Why this other one is 2 to the 2, which is, that's why it can represent 4 values. And then this one is 2 to the 3. What do you mean? So that 2, because we're using zeros and ones. So that's like, you're saying that how many? Yeah, that's the base. So like since f of x now has just one variable, but that variable can be either 0 or 1. So that's why we're using 2 as the base. Every variable is either 2 or 0 or 1. Always 2 possible values. right? So you just 2 to the number of variables to get the size of the set. Then once you get the size of the set, you can now iterate from 0 to its size and then convert each element to binary. Does that make sense? Sure? So now let's look at interpolation of multilinear polynomials. Cool? So this one we're going to be given a set of points, and then we're going to use those points and Lagrange interpolation to get back the original multilinear polynomial. But let's assume that we had an original polynomial. Let's say 2ab plus 3bc, right? It's a very famous polynomial. It's a very, very famous polynomial. And this is too big. Let's just do 2ab plus 3b, so that we just use 2 values at least for start. So, multilinear, right? This is multilinear. What's the degree? 2. AB, right? And then B. So let's evaluate this at a couple points that I want to interpolate. So we'll evaluate over the Boolean hypercube. Yes. So you know the same way, like when you have a degree 3 polynomial, there's another way to write it. You can write it as 4 points, right? So whenever you have a multilinear polynomial, the other way to write it is evaluating it over the Boolean hypercube. Do you understand? So if you evaluate over the Boolean hypercube, you have an equivalent representation.
This just like how you revert and express it in like that word things. So this also has like evaluation for
Yeah.
the functions and this still like that.
Yeah. So you will design that. No, we're doing Lagrange right now. But I've not started looking at representation and everything. Right? We're just looking at Lagrange for now. Okay. Yeah, I'm trying to get points that we'll use to interpolate.
Not represent.
No, not yet represent. Just to get points that we'll use to interpolate. So let's evaluate this over the Boolean hypercube. Okay? So that'll be what? F of what? F of what? F of what? F of what? So what's the output for the first one? What's the output for the second one? What's the output for the third? Wait. Let me do this slowly. Okay? So this is A, B, right? First one is A, second one is B. So wherever I see A in the original equation, we replace it with the value. And wherever I see B, we replace it with the value. Okay? So I'm just going to rewrite the equation, but I'll replace A with what it's supposed to be. So this is supposed to be 2AB. A here is what? So 2 times 0, what's B?
0.
Then plus 3 times B, what's B? 0. So 2 times 0 is what? So that first term is just 0, right? Then 3 times 0 is what? So everything is 0. Make sense? Then next one, 2, what's A?
0.
What's B?
1.
What's B?
1.
So that's what? Right? Does it make sense? Mitch, does it make sense? Okay. What's A? What's B? What's B? What's the answer? Make sense? Then 2. Right? So that's 2 plus 3, that's 5. So now what this means is that we have 4 points. And with these 4 points, we should be able to get back that polynomial. Because we have evaluated over the Boolean hypercube. Yeah. Yes, because of it has just 2 variables. So it has 4 points on the Boolean hypercube.
So according to what you say, first of all, we need to just know the number, the degree.
The amount of variables, yes.
So the amount of variables, 2 variables.
Yes.
Then the degree is 2.
The degree is 2, but you don't care about the degree yet.
Yeah, but for us to know the point that we're going to evaluate, it's going to be like 2 raised power 4.
2 raised to power number of variables, yes.
So now we know that 2 raised power 2
Yes.
is 4, so we know that we have to evaluate
Yes,
that.
yes.
So we have like
3 variables. It's 2 raised to power 3.
Yes.
Yes. So it's also the same thing as just enumerating the Boolean hypercube of that length. Yeah. Any other question? Alright. So now this is where you guys come in. So I'll show you the points now. Okay. Yeah. Which 6? Try my handwriting. Where is it? Yeah, 0 plus 0, sorry. Good? No question? Alright. So now these are the points that I want to interpolate. Want to interpolate 0, 0. You know before when we're interpolating, it was always like x, y. Now our x is bigger. It's now multiple values. So it's now comma, you get. This entire thing is standing in for our x, or for our interpolating set, right? While this is the y value. Okay? Yes. So these are the points. This is sufficient enough to represent that. Meaning that from this we can get this, and from this we can get this. We know that we go from a polynomial equation form to points via evaluations, right? So you evaluate the polynomial, you get the points. And we know that we can go back through interpolation. So this is evaluation right now. Now we need to figure out how to do interpolation. So what are the ideas? Just know that it is similar. It's similar to what we did in univariates. So just try and combine ideas and make certain suggestions. So once again, a new polynomial f of xy.
From those points.
Yes, from those points.
I think that, first of all, the way we did, then, like after evaluating it, then we have function of x equals to the result of the evaluation from the Lagrange.
Nice. Yes.
So then we'll now be able to find out what makes, what select each of the values
Mhm.
in the Lagrange.
Selector.
Yeah, fact that each one is known, the other one is zero, and to be cancelled out.
Yeah. Makes sense. So what she just described now is how do I put it? The general form. That's using the previous insight, right? So it's the same thing, f of xy is going to be equal to the output times a Lagrange basis. So here the output is 0 times L. But now L is selecting two things. Selecting 0, 0. You get? So L of 0, 0. But then selecting what? Is a polynomial in 2 variables. So your L2 will also be a polynomial in 2 variables. Then you have plus 3 times L of 0, 1. Right? Then plus 0 times L of 1, 0. Then plus 5 times L of 1, 1. Does this make sense? And the behavior of this L function is exactly the same. Interpolating set is the Boolean hypercube of length 2, right?
Yeah.
So the interpolating set is actually 0, 0, 0, 1, 1, 0, 1, 1. So now this first L function, if you pass in 0, 0, what should it output? 1, right? Because of it selecting 0, 0. But if you pass in any other thing, what should it give? Exactly the same idea, right? Then likewise, that's 0, 1. If you pass in 0, 1, 1. If you pass in any other thing in the interpolating set, it will be 0. So that way, it selects for the correct output. Because if you pass in 0, 1, this will turn to 0. The third one will turn to 0. This last one will also turn to 0. Meaning that only that middle one, the second one, that's 3 times 1. So the output is going to be 1, which is what we wanted. Like, the output is going to be 3. Sorry, right? I don't know if you guys get what I mean. So that's why I do f of 0, 1 now. So this is going to be 0 times. Now this first one is looking for 0, 0. But you're giving it 0, 1. So it's going to turn to 0. So that's 0. Right? Then 3 times, it's looking for what? 0, 1. And you give it 0, 1. You get 1. Then plus 0 times, looking for 1, 0. You give it 0, 1. 5 times, you're looking for 1, 1. You give it 0, 1. So at the end of the day, you have 0 plus 3 plus 0 plus 0, which is equal to. Does that make sense? And so
I'm confused, please.
okay. Do you know where you're confused?
Yes.
Okay, where are you confused?
So, like this, when you're doing the f of 0, 1, when
Yes.
you're doing that stuff,
Yes.
like how you're getting those
Yeah.
values you're putting in there.
Okay, okay. So I've not told you how to get this L function.
Okay.
I'm just telling you the behavior that we expect the L function to have based on the previous univariate. But even though you don't have the previous, the behavior is still the same, okay? So the idea is that we want, when you evaluate it at 0, 0, it should give you 0. When you evaluate it at 0, 1, it should give you 3. When you evaluate it at 1, 0, it should give you 0. When you evaluate it at 1, 1, it should give you 5. So what we do is that we put the outputs, right? And then we multiply them by, we call them Lagrange basis polynomials. Or you can think of them as selectors. So now the behavior of this is that if you put in what it is looking for, it will turn to a 1.
1.
And if you put in what it is not looking for, it will turn to a 0. Right? So now, let's say we wanted to do 0, 1. We want the output to be 3, right? So we only want that one that has 3 to remain.
Yes.
The other ones, we want them to disappear. And we make them disappear by turning these guys to 0. And because of the behavior that we have described, they will in fact turn into zeros, right? Because they are looking for something different from. So you put 0, 1 here, and you look for 0, 0, it's like 0, right? So it's only that guy that has 3 times this that will be 1. So that's why we have 0 times 0, 3 times 1, 0 times 0, 5 times 0. And at the end of the day, the answer is 3. Does it make sense?
Yeah. Oh, that 5.0 is like dot.
Times 0. Yeah, times.
Okay, oh.
Oh.
Yes, I was saying 5.0.
Oh, so all of this has been multiplication, no?
Yes, so I understand that part is multiplication.
Okay,
because
okay.
It's 0 dot.
Yeah,
L.
yeah, yeah.
But when you go to 0 dot 0, this is a number dot a number. So it's looking like a.
It's multiplication. It's multiplication. Okay. Does it make sense?
Yes, it does.
So this is exactly the same as univariate. The only place that it's now be different is now figuring out how to generate the Lagrange basis. I don't know how to generate the Lagrange basis. I've forgotten how to generate the Lagrange basis.
You say you don't know how to do it.
I don't know how to generate the Lagrange basis. Like I've forgotten how to. So we'll have to like figure it out by ourselves today. It has been a long time. So we want to generate L. So you guys, how do we create a function that takes in 2 inputs and 2. So if you look at it now, it's like x should be something and y should be something.
Like the formula
What do you mean by formula?
of getting the Lagrange basis, like mathematics.
What is your formula?
The
It's not enough. It's okay. It said Friday said that you must give us your why. Why the formula works.
You can do the proof actually.
There's a proof for it.
No, intuitively explain to a layman what your how to get it.
Okay. Maybe let me write the formula first.
Oh yeah, yeah.
I'll explain later.
So tell me before I
So
write
we
it
have
down.
a
Product. Okay.
Of, I starting from 1 or from 0 to n. Open a bracket. Xi yi plus open another bracket 1 minus xi 1 minus yi.
Yeah, explain.
Okay.
You can't explain. But you get formula. So technically this is correct. Like this is how you would do it. But we'll explain exactly where all of this came from, right? From first principles. But this is technically correct. But you just can't formula. It's not good. So we'll break it down. Yeah, this is the compact form. Mitch, you like that one now? You like the compact form? Alright. So let's think about this thing, right? We're trying to create some kind of an equation, right? That so interpolating set is what? 0, 0, 0, 1, 1, 0, 1, 1. We want to create something that if it sees one of them, it will turn to 1. 1. So that's like L of 0, 0, right? So in this function, if it gets 0, 0, it will give out 1. But if it gets any other thing here, it's supposed to give out 0. How would this work? So the first thing is like, let's simplify the problem a bit, okay? Rather than 2 variables, let's imagine it was 1 variable, right?
That's what?
1 variable. So let's say the interpolating set is just 0, 1, okay? So now we want a function that, if it sees 0, let's say we do L0 of x, right? So if it sees 0, we want it to give us 1. But if it sees 1, we want it to give us 0. Jude, okay, no. 2 of you. Now, who can come up with a formula that can do this? Oh yeah, it's irregular. Exactly. So what she's doing now is like regular Lagrange. Because it's technically like a univariate poly, kind of, right? So 0 is what we're looking for, right? So we don't do x minus 0. We do x minus every other thing. So it's going to be x minus 1 divided by, then you evaluate what? Yes, you evaluate x at 0. So that'll be 0 minus 1. So what does this mean? X minus 1 divided by minus 1, which is equal to 1 minus x. So this is something that you can test it, right? So let's evaluate this at 0. So L of 0 evaluated at 0 is what? 1 minus 0, right? Which is 1. It looks for 1. It looks for 0. It saw 0. It gave 1. Does that make sense? Then if we do the same thing, but we use it on 1, then we're going to get what? 1 minus 1. So it's not looking for 1. Hence it gives us 0. Does that make sense? Cool? Now let's do the same thing for L1. So what will L1 be? Does that make sense?
Why is there one of this?
Huh?
So you are looking for
L1 of x. So we're looking for something that, if it sees 1, it will give us 1. And if it sees 0, it will give us 0. Does that make sense? Just by even saying it, you can figure out what you don't even calculate. Like if you put 0, you should get 0. If you put 1, you should get 1. X. Like what? It's just duplicates the inputs. Does that make sense? But let's still use the Lagrange. So we'll do x minus
0.
the one we're not looking for, right?
Yes, 0.
Divided by 1 minus 0, which is what? X divided by 1, which is what? Does it make sense? So now we have something that can look for 0, and we have something that can look for 1.
Are you not saying you not them together?
Maybe. Is it clear? Sure? Go.
It's not clear.
Okay. Sure. When you say again, where is the starting point? Which point?
Yeah, we are evaluating this.
From here?
Yeah.
Okay. All of you. Where should we start from?
Okay, you just wipe some.
No.
Why are we coming back to this last guy
The
here?
L1 of x.
The L1 of x into x minus 0, 1 minus 0.
Yeah.
Yeah, why are we coming
So-
back to that?
Let me start afresh. So we'll start from the problem now. So we started with the problem of we want to create a polynomial that can search for multiple numbers, right? So that's why we want to create a polynomial that can search for 0, 1, right? It takes in 2 inputs. This is our goal. This is the target. Because once we have this, we have solved Lagrange interpolation for multilinear. Like we'll just get it and then just put it in here and we're good. But the problem is that it's not so obvious how to do it directly. You give a formula, but that formula is not obvious why that works, right? So what we're now trying to do is, this problem is hard, and when the problem is hard, you simplify, right? You simplify it to work on something smaller and see whether that gives you some kind of insight that might help you solve the larger problem. So we now reduce the problem to, let's create something that can search for just 1 bit, right? Either 0 or 1. So, because we're working over the Boolean hypercube, so it's always 0s or 1s. So we're saying, okay, can we come up with something that can look for 0? And can we come up with something that can look for 1? So L0 of x is something that is looking for 0. And then L1 of x is something that is looking for 1. But then this is very similar to univariate polynomial, right? Univariate polynomial always has some kind of L that's looking for something in interpolating sets. And it's always a single variable. And how did we do that? Remember that we said that if we want something to be 1, we need to do a over a. That will give us 1. And if we want something to be 0, we need to do 0 over a. That will give us 0, right? So we want to do the same thing here. Right now, our interpolating set is what? 0 and 1, right? Single variable, 1 bit, 0, 1. So if we're looking for 0, so in this case now, L0, we want that if you give it 0, you should get what? 1. And if you give it 1, you should get 0. So let's deal with the 0 case. If you pass 1 here, sorry, we'll deal with the 1 case. If you pass 1 here, 1 is to be 0, right? So that means that the top has to be 0. Does that make sense? So how can you make the top become 0 when it sees 1? Right? You do x minus 1, right? So this is going to be x minus 1. So now if x is 1, the top is 1, because 1 minus 1 is going to be 0, right? But then what happens when we put in 0? If we put in 0, the top is going to be what? 0 minus 1. But 1 to be the output. What does that mean? It means that the top has to be the same as the bottom whenever we see 0. So how we do that is that we just divide by what it will have been when 0 is passed in. So we divide by 0 minus 1. Does that make sense?
Yeah.
So if we pass 1 in, the top will turn to 0. So it doesn't matter what is on the bottom, right? It will be 0 divided by something, which is always 0. But then if we pass in 0, it will now be 0 minus 1, but the bottom is also 0 minus 1. So it's perfect. So it's if it sees anything here, it will become 0. But if it sees this, it will become 1. Does that make sense?
Yeah.
So we're now using this idea to figure out a polynomial that if you pass it 0, it will give you 1, and if you pass it 1, it will give you 0. Does that make sense? So that's what this is. So at the end of the day, it's now like x minus 1 divided by what? Minus 1. Then when you divide by negative, you can switch the sign. So this is 1 minus x. So this is something. So what we call it check 0. A function that checks for 0, right? You can also call it L0 or something, but we call it check 0 just to make it easier to communicate. So check 0. So this is our check 0 function. It checks for 0, right? Then we now do the same thing for L1, something that checks for 1. So if we're checking for 1, it means that if we see 0, we want it to be 0, right? So if we see 0, we want the top to be 0. If that's the case, then that means that the top has to turn to 0 when we see 0, right? And that's what? X minus 0, right? It's always x minus what you want to destroy. You want to destroy 0, so it's x minus 0. Then the question is now, okay, what if there's a 1? That means that you just need to put whatever it would have been underneath, right? So that's going to be 1 minus 0. Right? You just evaluate the top at 1, and you get the bottom. So at the end of the day, you just have x divided by 1, which is equal to x. So this is check 1. Does it make sense? Cass? Good?
So we are basically checking for 0 and 1.
Yes, in an interpolating set of 0, 1. Do you get? So now that we have this, does anybody see how to get this? So we have, this was the goal. But it was something that can get 0 and 0, 1, right? But it was too hard, right? So we reduced it down.
You combine the two functions.
Yeah, I'm coming. So we reduce it down, right? To L0 of x, something that can check for just 1 bit, and something that can check for just 1 bit, right? This one can check for 0, this one can check for 1. What are you saying?
So,
Combine
combine
the
like
functions.
How you combine the two functions?
you know, it's 0.
So when this one is, we were actually checking for 0.
Yeah.
Was x minus 1,
1 minus x.
0 minus there. So yeah.
Mm-hmm.
No, I'm even starting from here, from this very first one.
Mm-hmm.
So you can just combine the two functions.
How?
So what is going to be like if you have 0, 0, it will be 0. So you have 0, 1, it should give you 1.
Yes. And if you have 1, 0, it should give you 0. 1, 1, it should also give you 0.
So just like you said, just combine them like through multiplication.
Combine. So how would that look like?
So it will be, so for the first part now, you know that the top and bottom, like multiply them together.
Combine the basis.
So you're saying I should what?
Do x minus 1 over 0 minus 1,
Uh-huh.
then multiply like,
Uh,
then x minus 0.
so I can just do the result now, right? Like
Yes.
1 minus x times x. Is that what you're saying?
Yes.
Is this correct?
We test it and see.
1 minus x squared.
No, x minus x.
Sorry, x minus x squared. There's something missing. You guys have just one thing missing.
The only thing that is missing is the y
Yes.
part actually.
Yes. So this function was L of xy,
Y.
not L of xx.
Yeah, that's
So-
what I wanted to point out.
Yeah. So the x now, right, is looking for 0. So this means that you check 0 for x. Then you check y, 1 for y. Do you get? We'll do an example. So
Okay.
if you interpret this well, you realize that it's just saying that x should be 0 and y should be 1. Whenever you have and, both sides must, yes, multiplication, both sides must be true. So let me draw the truth table for and. Let's say AB, right? So this is like 0, 0, 0, 1, 1, 0, 1, 1, right? So the truth table, like when both of them are 1, 1, then the answer is 1. But if any of them is 0, then the answer is 0. This is equivalent to multiplication, right? 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. Not 6. And 1 times 1 is 1. This math is sweet.
I say if it's available.
So this is and, right? So just like this must be present and this must be present. You can encapsulate that with multiplication. Does it make sense? But we are saying this must be present or this must be present. Then encapsulate that with addition. So if you somehow wanted to make a polynomial that x could be 0 or y could be 1, then you most likely have to use like addition. I don't know where that will ever come up, but when you understand it deeply, you can now like make tweaks. So let's now create this L of xy that can find 0, 1. So remember, our check 0 is 1 minus x, and our check 1 is x. Now we are creating something that is L of 0, 1, right? But x, y. So what are we doing? We're saying check 0 for x and check 1 for y. So
That's sorry, C1.
yeah.
It's not supposed to be CY, like we're checking for Y there.
So I'm just giving the general formula for check 1. So you now replace it with the variable that you actually want to check. So this now is like you're checking 0 for x, right? So it will be C0 of x times C1 of y, which means that you can now rewrite it as just 1 minus x, right? Because that one is times y. So this means that this function is just y minus x. So what I'm claiming is that this function, if you evaluate at 0, 1, it will give you 1. But if you evaluate at any other point on the polynomial curve, it will give you 0. So let's test it out. So if you evaluate at 0, 0, this is xy, by the way. So this is 0 minus 0 times 0, right? Which is 0. If you evaluate at 0, 1, this is 1 minus 0 times, times 1. Sorry. Let me just write it on top so that it's not confusing. Right? So this is what? If I raise at 1, 0, that's going to be what? 0 minus 1 times 0, right? Which is 0. If I raise at 1, 1, that's what? 1 minus 1 times 1, which is equal to 1 minus 1, which is equal to 0. Does it make sense? So you can see that we have been able to get the function that can get 0, 1. Does it make sense?
Yeah.
You sure? It's not supposed to make immediate sense, yeah.
Is it because we use the other polynomial to get that 1 minus x, or it's just generally 1 minus x when you're checking for 0?
So when you're checking for 0, if the interpretation says it's 0, 1, if the interpretation says 0, 1, it's just 1 minus x.
What if it's not 0?
If the interpretation says not 0, 1, then you get another. Yeah. But for us, multilinear, interpretation is always 0, 1. Does that make sense? So let's say we wanted to get 1, 1. It's looking for 1, 1. What would that look like? Yeah.
Check 1 for x, check 1 for y.
Yes. Check 1 for x, check 1 for y. And what's our check 1? It's just the symbol, right?
Yeah.
So it's just going to be x times y, which is xy. So this is looking for just
Sorry, can you
yeah.
no, yeah.
Yeah. So if you have questions, it's not supposed to make like perfect sense, but you said? Polynomial. So it just depends on like yes, or even if it's like 3 variables. So let's say I want to check for 0, 1, 0. 1 minus x, y. No, they have to be different now. Then 1 minus z, exactly. So that's how you can get, yeah.
No, at the start, you first put the polynomial with 3 variables.
Yes.
Now, I'm sure to have a different formula.
No. Exactly the same.
So
Yeah. Because we're only checking in Boolean, in 0 and 1. Remember the multilinear is over 0, 1.
yes.
So I'll do it for 3 variables now, so that you can see.
The same step.
Exactly the same thing.
I'm saying the formula what we derive might be a little bit different.
What do you mean derived?
Like when we go through all these steps now.
You mean like the form? Wait, what do you mean?
Three variables this time, it will be just it will be x and y next time. So
Yes, be x, y, z.
yes. The main question I thought was we want to like easily account for in our programs when I write when I write comments. We want to account for different
Yeah, you have the number of variables. Don't worry. When we get to, we'll do design now. We'll do implementation design. Where we'll try and figure out how to implement it actually. Is it making sense? Is there any question?
It did not make sense that because, like, you said alcohol, you have to
Sorry.
convert it to various, like, bring it to normal 0 and 1,
Uh.
bring it up a step up
Uh.
by splitting it. Like, I'm just thinking about, like, we now carry it to 2 x, y, and that's when you multiply it. I know that the first one will be x, and the other one will be evaluated at different things.
Are you talking about like a potential way to implement it? Maybe. Yeah.
So, I'm trying to get like a mental picture of all of this.
Yeah.
So, you know,
This guy.
the general reason why we are trying to do this is okay. We have our like you said, we have our y.
Yeah, we have our
Y
y's.
value. So, when we have something like 0, 0, and
Yeah.
we have 0, so we want to make interpolate it in such a way that when we see 0, 0, we
Yeah.
get 0,
Yeah.
right? And
We get
have-
one. We get one.
Huh?
You're talking about this one, right?
Yes,
So when we see 0, 0, we should get one.
we should get 1.
Because
Which
that's-
when you multiply by 0, it gives you 0.
And that one gives 0. Yeah, the output.
Okay, now we are not dealing with
We're not dealing with the y's.
for now.
We're just teaching you how to generate the Lagrange basis.
Okay,
You get?
okay.
Then when we're done, you will now input them in here and do like a multiplication plus. That's the dot product.
Scroll down.
Yeah.
Yeah, down. Yeah, scroll up. Yeah, yes. So, here we are doing 0, 0, and we are like substituting the 0, 0 value, that's the xy values into that y minus xy. And we are getting 0, 1, 0, 0. Like this value, what we are getting, I can't have a mental picture of where we want to use it here. Is it that we are still going to substitute it somewhere?
No. So, this one now,
Yes.
this is a function.
Okay.
If you take 0, 1,
Okay.
it's going to give you 1.
Okay.
If you take any other thing in the Boolean, it's going to give you 0.
Okay.
So, this one here,
Yes.
I'm just showing you that it actually does what we say it does.
Oh.
Okay.
Okay, makes sense. So
We
what
now-
we are doing here is we are like testing
Yes.
for 0, 1,
Yes.
and
And-
we are okay.
And you can see that it gave you 1.
Yes, and it's okay.
And it gave you
every other
0
one is
everywhere.
turned off.
Yeah. So,
Okay.
the behavior is correct.
Yes.
So now we'll take this y minus xy
Yes.
and then we'll go and put it here.
Okay.
So it's now be 3 times y minus xy. Do you get?
Okay.
We'll also
Now-
do
now get for this one.
yes, and for that
look
one, and
a
for that
way
one, and
to
for that one.
simplify
Then we'll
everything.
simplify everything.
Okay.
And the hope is that when we're done, 2ab plus 3b.
Yeah.
You understand?
That makes sense.
So we're not supposed to be using xy, we're supposed to be using like a, b.
Yeah.
But it makes sense, right?
Yes.
It's the same with univariate.
Yeah.
It's just the way we generate the L function is different.
Sorry.
Make sense? Any questions? Alright, so what do we do now? Yeah, let me show you how you can do this with 3 variables or 4 variables. So let's say we wanted to get an L function for 3 variables, x, y, z, right? Now this function, let's say we wanted to get 1, 0, 1. 1, 0, 1. Check 1 is what? X. And check 0 is what? 1 minus x. So this means that x is supposed to be what? 1. So we're supposed to check 1 on x, which is just. Then y is supposed to be what? 0, right? So we're going to check 0 on y, which is what? Then z is supposed to be 1, so we check 1 on it. You get? Then we multiply through. This is x z minus x y z. So now, the claim is that this thing we're looking at here, if we evaluate it at all possible Boolean hypercubes, like 3, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, if it's like that, only one place will be 1. And that one place is going to be. So let's do 1, 0, 1. I don't know if I can do everything though, but we'll do 1, 0, 1. So 1, 0, 1. This x, this y, this z, right? So x is 1, z is 1, x is 1, y is 0, z is 1. So that's 1 minus 0, which is equal to 1. Now let's just randomly pick one of them. So let's say we did 0, 1, 1. This x, this y, this z. So x is what? 0, z is 1, minus what? X, 0, y is what? 1, 1. So this is just like 0 minus 0, which is equal to 0. Does it make sense? So this is how you can do it for any. Yes. So by just looking at the binary string, you can come up with the appropriate polynomial, as long as you know how to check for 0 or 1. Does it make sense? Cool?
Question.
Yeah.
So can you go to the evaluate the check?
Which one? This one? Just tell me when to stop.
Okay, here.
Here?
Yeah, I think it's here.
What are you looking for exactly?
I want to see how you evaluate checks.
What checks?
Check 0 and check 1
How I got check 0 and check 1?
Yeah, the value. The expression.
That's this here. So this check 0, this check 1, based on univariate Lagrange interpolation. So interpolating set is 0, 1. Does it make sense?
Yeah, it's fine.
But this is supposed to be L of X, L of Y, L1 of Y.
No, it depends on your variable. So this one, I was just getting the general formula for checking 0 and checking 1. But then, depending on the context you're checking it, you now choose the appropriate variable name, right? So, do we understand multilinear Lagrange? If you understand it, please raise your hand. Not completely. That's it. Just Cass, do you understand multilinear Lagrange interpolation? No, sorry. The Lagrange basis generation. Okay. So let's do one example with the full Lagrange interpolation. Okay? Maybe that will make some sense again. Okay? So those are the points we want to use. The goal is to get back 2ab plus 3b. If we don't get it back, then we have messed up somewhere. So let's start. Okay? So we're trying to create a two-variable function, ab, right? So f of ab is going to be equal to something, right? We don't know the full structure of that thing, but we know that it's going to be the output times the corresponding Lagrange basis. So let's do the output times corresponding Lagrange basis. So this is 0 times, L of 0, 0, AB, right? Since we're using AB now. Then plus 3 times L of 0, 1, right? Then plus 0 times L of, and then plus 5 times L of. So now we can already remove 2 terms, right?
Yeah.
Because like 0 times the first one is going to be 0. So we don't need to waste time calculating that, right? And likewise, the third one, 0 times, we don't need to waste time calculating that.
Even if it returns one.
Yeah, even if it retires or it returns. Wait. We want to do a full example now so that you guys don't miss. Okay. So what we're saying now is that this is going to be the output times the Lagrange basis, right? So 0 times something that looks for 0, 0. Then 3 times something that looks for 0, 1. Then 0 times something that looks for 1, 0. And then 5 times something that looks for 1, 1, right? But the thing now is that you can see this term here. This term here is already 0 times something, right? So that means that we don't need to waste our time calculating the Lagrange basis there. It should just be 0, right? So I'm going to do a reduction now so that we don't. Then we might do another example that doesn't have something like this. It was me that picked the values of this thing. So if I reduce it now, then if you want, you guys can try it. You guys want to try yourself first? Yeah. Yeah, you guys try yourself first.
Yeah.
I'll just time it or something. Then we'll now do it by ourselves after. But just attempt it. No, by hand. So the idea is this, right? You just solve for all the L's using check blah blah blah. And then you input it back in and multiply everywhere. So see if you get back 2ab plus b or something. You just tell me whatever you get. I will know if it's correct. You have done it?
Yeah.
Who has done it? Yeah, let's just wait for a bit. Yes, do it. Let's try it. Don't let me know.
So the starting point.
I'll come and check. this.
Okay, regardless of whether one or something like this.
So the interpretation is 0 and 1.
No, not 0 and 1, 0 and 0.
Yeah. But asking why you check 0 and 1. And you check 0 is coming from set of 0. So you check 0, check 0, check 0, 0. So these are going to say that x should be 0 and y should be 0. So we are doing x 0, 0. I'm checking the
So He's the one that wants to choke. He's that one that will make you choke.
Alright, let's continue. Yeah. Got to that. Okay. So we'll just do it quickly. So we're ignoring the ones that have zeros, and it's just going to be 3 times something, right? So while a is supposed to be 0, which means we're doing check 0. So that's what 1 minus a, and b is supposed to be 1. So that's just b. So this one is even simpler than univariate Lagrange, because univariate Lagrange, you cannot just be writing it out like this. This one, I don't even need to solve it somewhere else first and then bring the output. I can literally just write it like I'm reading. Then this is now plus. The other one, we don't care about that, right? So we're just going to 5. So 5 times. A is supposed to be 1, so we're checking 1. And b is supposed to be 1, so we're checking b. That's basically it. So this is like 3b, 3ab, 5ab. That's what 3b. Make sense? Yeah.
You say that like this one is not like you can just introducing the value. Given that like we've gotten our L of L of 0, L of x at 0 and L of x at 1. Like
Check 0, check 1.
yes,
Yeah.
so we don't need to kind of all this complex. Like we can just put our variable whenever we see, whenever we have like zero, we put this one. My question is, what if we have more than this number of points?
What do you mean?
Like like 4 points.
Oh, okay. So I think I did an example here. Alright, like see, this one has 3 variables. So x you're checking 1, y you're checking 0, and z you're checking 1. Checking 1 is just writing the variable. Checking 0 is 1 minus 8. So that's what you have there. So this thing here, if you evaluate at 101, you get 1. And if you evaluate at any other thing, you get 0. Does it make sense?
You were like trying to implement it, but you just stop all this exam.
If you're trying to implement it.
Yeah. If you just stop the evaluations as
So what you could do is that you could have like something for check 0 and check 1, yeah. Then you just use the bit string too. But it's not that straightforward. You guys will still need to design your representation and everything. So, Stop. But does it make sense so far?
Yeah.
The coding will. Good? Does it make sense? Half. Were you able to solve it? So, do you have
It's
any?
just not understood when like check 0
The variables, yeah.
check 1,
Yeah.
check 1.
Yes. So it's like I'm reading the bit string. And like, okay, 110 is check 1, check 1, check 0. And then you use the accompanying variable to.
So in the next one, why is it?
So
why
because
is
so no this check 1. So check 1 is just put the variable back.
it? So this was you saying at 101.
Yes.
Now it was at 100.
Yes. So that is at 100. That's going to be what?
X minus y.
Makes sense.
And then when you expand it, you get
Yeah, the poly. Yeah. Makes sense. So that's univariate. I think we're done.
Let's do that for the example of that. 2 degrees of the mass for
Oh yeah, that's the so you want us to interpolate it. So we need to get points on it first. Then we'll go back. Let's do 1 3 variable example. You guys don't need to do it, or you can do it. If you want to do it, do it. Well. So let's use this formula. Right? How many points do we need to get for this?
2 is 3.
Yes, that's 8. So once you get 8 evaluations, you have like the full representation. Yeah. So over the Boolean hypercube, 0 0 0. So you can build a 2. We built a 2 because this is so annoying. Yeah, we built a very crude 2. In fact, let's just use that now. Where is it under? It's under like rapid experimentation something, right? Yeah, rapid iteration tools. Product ML, algebra, gradients. I think it's the first one, right? Yeah, it's probably the first one. So, how do you uncomment? I've forgotten. I'm coming. You said? No, I want to generate the Boolean hypercube. How do I uncomment this? Control forward slash. Okay. Grassy. So this is what we used. We have something that can generate the Boolean hypercube for us.
So did you write this?
Yeah, that was a while ago.
Huh?
Why did you frown?
I didn't proud.
You shock am.
I was just amazed.
So let's say we have three, right? Three variables. So this is where we'll now put our polynomial, but in like a function form. What was that polynomial again? It was 2ab plus,
3ABC.
yeah, so it's 2 times a times b plus 3 times b times c, alright? And then we can generate the Boolean hypercube of length.
I thought the A, B, and C are supposed to be defined in compute.
Oh, I did ADE, right? That's what you meant. Good. What's the problem?
Like 5.
Oh,
Yeah, comment that.
so it's not even, we didn't even build it well. We just, it's so crude, but you can actually make something that is really good. So now you can see like all the evaluations over the Boolean hypercube. So that's what I was about to do by hand. This is basically it. Yeah, you can use it for 4 values. You can use it for as many values as you want. But I don't want to interpolate 4 values.
Just package.
You want to do 4 values. That's 2 what? Give me a 4 variable polynomial. So like f of a comma b comma. That'll be what? Let's say 2a plus 3bc plus 4d. Alright? So I'll generate a new one, so I won't delete that one because I want to use that one.
Not equal to
Yeah, that's just a comment. This can be made way better. Like this is just crude.
When it's into a package.
Exactly. So we just write our polynomial. 2 times what? A plus 3 times b. Right? Oh, I get what you meant by use equal to. Plus what? 4 times d, right? Then all we need to do is just call it in the main. So I'll just duplicate this. So we'll just generate the Boolean hypercube of length 4. And then we just put it. Don't worry, when I get back home I'll make it better. I'll make a better one. Right? So when we run this now. Thank you.
The other one,
Which one?
there should be a comma. It's supposed to be a comma there. You're computing the second, the compute instead of the compute.
I'm what?
Use this computer.
The function.
Thank you.
yeah.
You get? So imagine if we had to do this by hand. And we have to evaluate every single one to be crazy. So now we can just use this and then just interpolate on top. So I can hide the formula itself and just give you guys the points and ask you guys to do it and see if you guys can get the same thing. So huh? Yeah. What is it?
All those numbers in front of them.
This one's at this side.
No.
The other ones. They're the evaluations of 2a plus 3bc plus 4d at those points. So you can see now, like if you do 0, 0, 1, right? It's only d that is 1. And this is the only place d is. So that will be 4. And that's how we have 4. All these other ones have zeros. Does it make sense? So compute. So let's do this one by hand. Sometimes this site is usually really slow. So this one now is just going to be 3 evaluations that we're going to do. 3 L values, right? Because they're just 0, 0, 0, 0, 0. And the goal is to get 2AB plus 3BC. Make sense?
Yeah.
So I'll just write it down so that we can. That's what 0, 0, 0, 3, 0, 0, 2, 5.
We can't see the.
Yeah, I'm gonna write it down here. And when I get there, we'll just use that. Okay. So let's try solving this, right? So we don't. Yeah.
The polynomial you run like checksum for 0 and 1.
Yeah.
Was it x squared minus x?
Which one?
Like where we got the whole checksum of 0 is 1 minus x.
That checks for what? 0 what? Yeah. No, the first question you asked, you said the one that checked for what? 0, 1. Is that what you said?
Yeah, I said like the polynomial used to like run that checksum stuff, like the Lagrange basis. Was it x squared minus x?
We're running where? The code?
Not code.
Not code. Okay.
Yeah.
Previously,
Yes.
When?
Like before we got like the whole when the checksum is 0, we have 1 minus x, and when the checksum is 1, we have x.
Yes.
Right.
We got that here, right?
Yes. I'm saying like what points were we interpolating? Like what points were we using for this? Basically.
This one,
Yes.
the interpolating set, is 0, 1, right? I don't know if I get your question correctly, though. But are you asking now, like, how
So
did we
what
get?
I'm saying is like we are basically using 0 when x is 0. we
Yes.
have- Is this 0 or when x is 1? We have 1.
So they have different behaviors, right?
Yeah.
This L0 is saying that when x is 0, we should have 1. And when x is 1, we should have 0.
0.
Yeah, because this one is looking for what? It's looking for 0, that's why. Then likewise, this other one, when x is 1, we have 1. And when x is 0, we have 0. Does that make sense? So like what they are looking for is subscripts. And whenever they see what they are looking for, they give you 1. But when they see something else, they give you 0. But I don't know if I got your question. Are you still confused?
Sorry, just for
So I think what it's saying is those that basis point, those points of 0 and 1.
The ones that have like this,
0
right?
and 1. Yeah, the interpolating points.
Okay, those
0 and
ones.
1. Yeah,
Yeah.
1, 1. So it's saying what is the equivalent polynomial for that?
Is that what you're asking?
Yeah.
What's the equivalent polynomial for that? That's not a polynomial.
You know you have to interpolate to get like. I didn't even get my point.
Which polynomial this start from?
I asked for the y value.
Yeah, I'm saying like to get the basis basically, you know we had to have like points to interpolate from. You get my point. Like when we were trying to get like the Lagrange basis from like interpolating points, we have just points and we use this to like get the original polynomial. Right? So I'm saying now you have
For
this-
multilinear.
Sorry, not multilinear. I'm talking about invariant now.
Okay. Continue.
Okay, so what I'm trying to say is, to get the whole like Lagrange basis for multilinear, we had to use like this checksum part from the univariate implementation, right? Now I'm saying, like, how did we get this? Like, what points were we interpolating from to get this to always know that when checksum of x
0.
is 0, we have 1 minus x.
Okay.
When checksum of
Okay,
when
okay.
checksum is 1, we have x.
Okay.
You get my point.
Yeah, I think I get your point. The interpolated set is 0, 0, 1. That's it. So wait.
It's confusing the points
With the interpolating set. Yes. That's what I think too.
Yes, I think that's one of
Yes. So here now we are just focused on the interpolating set.
not the point.
Like the Lagrange basis don't care about y. They only care about the interpolating set. So in this case, the interpolating set is just 0, 1. And then we just get the Lagrange basis. Then you cannot use the y values outside.
Yeah, so what you did, which was what we checked was now, was that that's the interpolated set. So it just look like, so we're looking for arbitrary y values.
Mm-hmm.
Arbitrary y values that if we interpolate on those points, give us the polynomial.
Mm.
Yeah, so
So
that
what
polynomial
you-
was x squared minus x. So
Okay.
yeah.
So what you're looking for now is a polynomial that when you evaluate at 0, it should give you something.
Yes.
So you choose your random y for that, right?
Yeah.
And when you evaluate at 1, it should give you something else. So you did that thing times check 0 plus that thing times check 1 to get some output. But what y's did you choose?
You choose. I used 1 and 1.
You use 1 and 1.
Yes.
Yes. So depending on the y you choose, it's going to be a completely different polynomial. So that x squared minus x that we're talking about is for 1 and 1. So f of 0 should be 1, f of 1 should be 1. But any other thing will be different.
So is it safe to say that now since you just talked about the interpolating set being like those tuples, right? So I know it's kind of like I'm rushing ahead, but I'm still trying to see the link
Between
between this and then the univariate. Because I know that we split these tuples into like x and y,
mm-hmm.
and then did the same univariate basis, Lagrange basis, same way we did it.
Mm-hmm.
So coming out to that interpolating set can also be split into two respective interpolating sets, one for x and one for y.
Yes. Then you now multiply them. Yeah. So it's like the two variables now like and. Yeah. Does that make sense? Okay. Let's now do that thing. This one. It's going to be really quick actually because most of them are zeros. Right? So f of what? X. No, A. A comma B comma C, right? So the output of this is 0. And all of these are zeros, right? So we don't care. So we're going straight to this. So it's 3 times L of what? 0, 1, 1. A comma B comma C, right? Then plus right? Then cool?
Yeah.
So we just have to solve it. So that's just what? 3 times A is supposed to be 0, right? So that'll be 1 minus A. Then B is supposed to be 1. Right? Then plus 2 times A is supposed to be 1. B is supposed to be 1. C is supposed to be. Then plus. Yeah, everything's 1, right? This does not look like the original polynomial. I won't lie. But let's solve it. So this is what? 3bc minus 3ab. ABC. I just did this one. Then plus 2ab minus 2abc. Then plus 5abc. Right? So this is what? 3bc. There's no like term. ABC, 3abc minus 2abc. That's like minus 5abc. Then plus 5abc. So there's no more abc. Right? So this is gone, this is gone, this is gone. Then plus 2ab. So you can see that this is exactly equal to this. Does it make sense?
Yeah.
So it's not hard. It's the same idea with univariate Lagrange interpolation. Cool?
But to complete this, you have to.
Implementation wise, are we?
No.
Okay.
You have to figure out.
So in ZK, right? This is how it comes. Like it doesn't come like this.
What's
Huh?
is that means
Yes. So usually like wait
Okay, the value.
So I'm coming. In ZK, you have like most of the time the current arithmetization process is that you want to do something, right? You want to do some computation. So let's say you wanted to compute Fibonacci numbers. So I am the verifier. I ask you to compute the fifth Fibonacci number. That's too easy though, but usually let's say I ask you to compute the 1000 Fibonacci number or the 1 million Fibonacci number. And I want to verify that without having to compute it myself for whatever reason, right? So what you have to do is you have to write each step that you are taking, right? One by one. So there's something called a trace. So this is how the trace will look like. You start with 1, then next thing is going to be 1, right? Then you do 1 plus 1, then you do 2 plus 1, then you do 3 plus 2, 5 plus 3. So this is like a computational trace. You are taking down each step of what you have done so far. Now, once you have this, you convert this to a polynomial. Do you understand? So what I'm saying now is that this is how it comes. It starts from the trace before it gets to the polynomial. It's not usually you have the polynomial first, then you now evaluate to get the points, and then you now interpolate again, which is just a waste, right? So this is how it's, you get the trace from the user, each step that the user has done, then you now convert it to a polynomial. Does that make sense?
Yeah.
So it's usually like this. So that's why, okay, no, that was a hint. It's usually like this. Make sense? So now let's say you now interpolate this. Let me now show you how you might prove something like this. So if you interpolate this, I don't know if this is a power of 2, but let's just assume you interpolate it somehow, right? Let's say, how many is this? 1, 2, 3, 4, 5, 6. Let's get to 8. This is 13, right? Then 13 plus 8 is what? 20 what?
21.
So let's say this is it, right? So this is the steps that the person took to compute Fibonacci. And you ask the person to compute the, this is the first Fibonacci number, or this is the first Fibonacci number, right? So first, second, third, fourth, fifth, sixth, seventh, eighth. So you ask the person to compute the 8th Fibonacci number and tell you the result. So the person now is telling you that the result is 21. But the person could have literally told you any number, right? The only way you can verify it truly is by also computing it yourself and seeing if what they told you is what it is, right? So what you do here is that you now create a polynomial out of this. So you can do univariate, for example. You can do univariate Lagrange interpolation of this. So the interpolating set to be 0, 1, 2, 3, 4, right? So you interpolate this, you're going to get a new polynomial called f of x, right? If you evaluate f of x at 4, why did I write it like this? If you evaluate at 4, you get 5, right? If you evaluate at 7, you get 21, right? But the provider is not going to send you this f of x. Because if they're sending you the f of x, it's as if they're sending you the full computational trace. And if you have to read everything, it's almost as if you have already done the work yourself, right? The verifier is so small, it doesn't have anything. So you don't want to send the full thing over. So now that you have f of x, you have a polynomial. What you now need to do is you need to create constraints on this polynomial. That's like something that must, a property that must be held. Are you good? A property that must be held everywhere. So what's this property? The property is that f of x for any x must be equal to f of x minus 1 plus f of x minus 2 for any x. I don't know if that makes sense. So let's say I want to do f of 5. So f of 5 must be equal to f of 4 plus f of 3. What's f of 4? 5. What's f of 3?
3.
And what's f of 5?
8.
It holds.
Yeah.
Left hand side is equal to right hand side. So the cool thing about polynomials is that even though the initial set was this, when you interpolate, every value of x follows this pattern. It's crazy. Like, let me interpolate. so annoying to interpolate. Well, that's it. So interpolate what? 0, 1, right? Then 1, 1, 2, 2, 3, 3, 4, 5, 5, 8, 6, 13, and 7, 21.
Now, I have a question.
Yeah.
Since it's
Whoa.
that is the question now. Since it's
Yeah.
how do we know the degree score?
No, it's the trace.
Okay,
The trace.
8
In our case, it's 8, yeah. Yeah. So it's supposed to be like a maximum of degree 7 polynomial, right? But now we can't even use this. This is normally we're supposed to be working with fields, and I'm not working with fields. But now what I'm claiming now is that if you evaluate this polynomial at, let's say, some x far off, and evaluate it at that x minus 1, and evaluate it at that x minus 2, and you sum it, it's going to be equal to each other. So this is now where error amplification comes in. Don't worry, we'll do it by, you guys should try it, sir. That's assignment, eh? So you guys should use your univariate polynomial interpolation, okay? You should create the points as I've done. Interpolate it and get a polynomial, right? Then pick a random field element, right? Then subtract 1 from that, and subtract 2 from that. Then assert that when you evaluate that polynomial that you got, at that point is equal to evaluation at the point minus 1 plus evaluation at the point minus 2. So the claim is that if the person did it correctly, right? If the person did it correctly, regardless of the x you choose, it will always match. But now if the person just made one mistake, just one, huh? I don't know what that is. But yeah, if the person made just one, oh wait, are you saying that, wait, Jude, are you saying that continuity is what makes it continue for all values of x?
Yes.
Interesting.
For every epsilon, like for any small interval around that.
So we enable
You guys will teach me after the class. I need to get that intuition. But now the point now is that if anything changes, now for most values of x, that thing would not hold anymore. I don't know if you are getting what I'm saying. So if the person is doing it correctly, regardless of the x you choose, it will match. But if the person did it incorrectly, almost all x you choose, it will not match. So that means that there is a really fast way to know if someone did something correctly or not. You just pick a random x value and check if that thing holds. If it holds, then the person most likely did it correctly. If it doesn't hold, then the person did it incorrectly. Does that make sense? This is how ZK is able to. So the verifier is not checking all of this. It's just saying evaluate your polynomial at these 3 values, and then you will check whether they are all correct. Once it checks that they are all correct, yes. So the verifier will say, okay, evaluate at 5, 4, and 3. Then they will send 5, they'll send 4, they'll send 3. And then you will just add it. And if it matches, it knows that the prover must have done everything correctly. But if it doesn't match, but now see the amount of work that the verifier has to do. It's fixed, right? It's just adding 2 numbers and doing an equality check. And then the prover could have computed the 1 millionth Fibonacci number or the 1 billionth Fibonacci number. It could have taken years or months or weeks. But the verifier will always only just do this. For what? The prover? That's why you have prover network. So prover network, they pay this thing, yeah?
This holds true for all polynomials, not this.
Yes. So as long as you have a polynomial constraint, they call it polynomial constraint. You can check the polynomial constraint at multiple points. But then there's this interesting property that if what you did is wrong, then the polynomial will fail everywhere. So it's like you can test the polynomial at multiple points. If something is wrong, even if it's a tiny thing that's wrong, then the polynomial will fail almost everywhere. But if the person did it correctly, then the polynomial will pass everywhere. So that distance, we'll talk about Schwarzschild lemma. Schwarzschild lemma is what powers this. That distance is exactly
What do you call it?
Schwarzschild lemma.
Oh,
Do you know Schwarzschild lemma?
can you spell it?
SCHWARTZ.
Okay.
I don't know if I spelled it right.
Answer is up.
This one.
It's
So this is what powers all of ZK. Literally all of ZK is powered by this. Like this is what powers all of it. Most of it, based all the ones that are based on polynomial IOP. Yeah.
Sorry, I didn't get the assignment.
What? Okay.
The way you asked.
So what I was saying is that Fibonacci. You saw the Fibonacci sequence, right?
No, the assignment. I didn't get the question.
Yeah. I'm saying you saw the Fibonacci sequence.
Yes, sure.
Yeah. So what I'm saying that you should use that as points, then create a polynomial that interpolates that, right? Then evaluate it at x. Choose a random x that is not in the point set, right? So you choose a random x, you interpolate it at that x, interpolate it at x minus 2, and interpolate it at x minus 1. Then add both sides and assert that they're equal.
You guys should do it like in a new. That's basically like a stack all over.
Exactly. This is how stacks. This is what stacks are based on.
Sorry, I know DK has a question. He said, is this formula now?
Yeah.
For polynomial, it is for what is it?
Fibonacci.
Fibonacci.
Yes. So the way ZK works is that you have some program, right? You now write constraints. So when you call ZK engineers, right, their job is just to write constraints. So this is an example of a constraint. This is something that must hold regardless of. So their job is just to write constraints. You get?
So, when you say we should pick these points now
Yeah.
and create a polynomial,
Yeah, interpolate it and create a
interpolate
polynomial.
it to
Yeah.
create a polynomial.
Yeah.
Now, if say I pick 4 points now, like 0
No,
to
use
4.
use all of them.
Huh?
Okay, once you
if I use all of them now,
yeah.
I'm just assuming, but let's say I get a 7th degree polynomial, right?
Yeah.
Now, you said I'm trying to understand where you now say we should
So-
interpolate again at
No, you don't interpolate again. So you have gotten f of x, right?
yes, like a 7th degree f of x.
Yeah, just yes. So this is the interpolation of all these points. So what I'm asking you to confirm for yourself is that if you choose any x, right?
You now
Any
evaluate.
yeah. So you evaluate it at that x,
Yes.
and then you ensure that it's equal to the evaluation at x minus 1 and f x minus 2.
Then that is evaluated.
Yes, you evaluate at 3 points and make sure that left side is equal to right side. Just test it for yourself for random values of x. Do you get?
Yeah.
So if the person did it correctly, if the person did it you can do both, right? You can do the case where the Fibonacci sequence is correct, right? And you can also do the case where the person made a mistake. Let's say instead of writing 8 here, the person wrote 7, or the person wrote 2. This strictly to Fibonacci. Yeah, this constraint is strictly Fibonacci. So imagine if the person made a mistake. Instead of using 8, the person used 7. You can test out yourself also. And then choose a random x, and you must verify that it's not equal.
But that was my question. This constraint,
Yes.
this one now is strict.
It's strict for Fibonacci. This is a Fibonacci. Yeah. This is a Fibonacci constraint. So you might be working in another problem that has a different constraint set. Do you get? And every program can be represented as constraints. Constraints on some polynomial or multiple polynomials. Every program has constraints that verify. So like this is not enough though. There's another constraint that we need here. We need to make sure that the person started from 1 and 1. Right? Because the person could have started from 5 and 9, but must have done the Fibonacci correctly. Right? He did 5 plus 9. But that's not what you were asking. When you were asking, you were saying that start from 1, 1, and tell me what the 7th or the 8th is. So that means you need another constraint. That's like f of 0 should be equal to 1, f of 1 should be equal to 1, and then f of x should be equal to f of x minus 1 plus f of x minus 2. Right? So these are the constraints. Then the person also told you what the answer is, right? He told you what the result is. So you also do f of 7 is equal to 21. So with all of this, you can verify Fibonacci for any length. So you just change.
At least 4.
Huh?
Does it have to be 4?
What have to be 4?
You need 0, 1.
So this is what you need to verify. You are talking about this, right?
Yeah.
Yeah. So you need to verify that the person started from where you wanted them to start from, right? So this is what this does. It verifies that the person started the Fibonacci computation from 1, 1. No, Fibonacci is just like take the last 2 and add it and get the next one, right? But what if the person started from 5 and 9, right? And you're saying I want the 7th Fibonacci number. Technically, the person will give you a 7th Fibonacci number and it will be correct based on where it started from. But you wanted the person to start from 1, 1. So this is what they call a boundary constraint. Like it checks the boundary of the problem. So this will check that it started at 1. This will check that it started at 1, 1, 1. Then this will now check that the person did each step correctly. You can see that it is variable, meaning that all steps. And then this one will check for the answer. The person said that when I was done, the answer was 21. So you check for where your answer is supposed to be. You were saying I wanted the 7th or the 8th Fibonacci number. But then you can see that the constraint doesn't change. If I now say compute the 1 millionth Fibonacci number, all I'm just going to do is f of 1 million is equal to what the person said. Does that make sense? But it's always 4 constraints.
But for that, for the Fibonacci, which we are going to like interpolate from the polynomial that represents it. So like how many values of the y do we need? Or is there, can we just just pick any 4, like in that order? So
Which one? Are you talking about this one?
yes. So we want to construct a polynomial. So we can pick 6 points and then to give us 5 degrees. We can pick 4 points. So
But you had an answer, right? Like you asked the person to do something for you, which is compute the 8th Fibonacci number. So that your answer must be in trace. You get? So usually they just stop once they have gotten your answer. Like why you compute more? You get? So if you wanted just the 4th Fibonacci number, then they'll stop here, I guess. Right?
so
Then they'll
then
just
we
use
went
this.
to verify it, we now use this.
F of 3 is equal to whatever they told you the answer is.
Because I was thinking of how they assign how it's like do about this.
So what you guys just want to test is test this. Like you interpolate and then you can evaluate it at multiple points.
Sorry.
You
The
said?
Fibonacci, does it start from 0 or does it start from 1?
We're starting from 1. I think it starts from 1, I don't know. Start from 0. Exactly. So you can start from 0. You can start from 0. Makes sense? Are we good? Any questions? Does it make sense? Are you guys tired?
No.
Oh, wanted to interpolate. Did we? No, we didn't. What done now? What?
My mind is on the multilinear.
Okay.
So I'm thinking of like how we can represent that in
What
code,
thing?
like in Rust.
Okay. You want to start doing design? Does multilinear interpolation make sense to everybody? Who doesn't understand it? You are. That one wants to go into.
You do not have to like start evaluating for that 0 and 1. You already know that if it's 0, you can just increase that formula. So that 1 minus x.
You are saying that you can write your check 0 and check 1
yes.
in code already.
Yes.
Yes,
Instead
you
of
can. Yeah. Like that's what we did now. So we had a function called check 0 that returns a univariate polynomial.
sorry.
We had a function called check 0 that returns a multilinear polynomial, which is just 1 minus x.
Okay.
Then we had another one for,
Okay, yeah.
so it just show you. Then we just, I'm already giving them too much information.
Well, I'm still curious about the
Implementation.
not even that
Hypercube. The Boolean hypercube.
Yes.
What are you curious about?
Nothing extra.
You want to understand it more?
Not understanding more. Just how to input. Like you have to
Oh.
this is gonna pay with the
Yeah.
because we
I don't want you guys to even implement
use your own.
coefficient form. Eh? No, don't use my own though, please no.
Wait, are we going to implement our own Boolean hypercube?
So it depends on how you do your implementation. I don't even know how you guys are doing your implementation. I think regardless of what they want to do, they will still have to implement. Regardless of the two types. Yes. The three of them. Right? So they are like three different stuff. I'm not mentioning it yet. But there's one that is like way better than the others for our purposes. That's the one that you guys must implement. But then the other two, if you are feeling ambitious, you can implement those ones. Yes. And you want to get into it. Yeah. So we did not know about the third way. When we're learning, we just went straight to the first way, the most obvious way. But it was so slow. I can't tell you the way yet. You guys have to figure out the way yourself. Then we now later figure out what the way was. Okay, yes. I talked about it to those guys. So, you know, the Boolean hype. Okay.
Yeah. So you'll be mentioning arithmetic.
Arithmetization.
So, like, what does it mean? Like,
So it means like you're converting. So ZK or snacks and stacks, they work with polynomials, numbers, maths, like those kind of relationships. That's the only thing I don't understand. So when we talk about like GKR, we're just talking about polynomials, or some check, we're just talking about polynomials. But then ZK promises that any computation can be proven. And any computation, you can prove any computation. It's Turing, like, regardless of the computation, you can prove it. So this means that, and the way to write computation right now with like programming languages, for example, right? So you can write it in Rust or whatever. So the question is, okay, how do you go from something you have written in Rust to polynomials? That missing part is what arithmetization is.
that's what? The missing part.
Yeah. So like expressing a real world computation as polynomials, that is arithmetization. And there are different ways to do arithmetization.
Expressing a real world computation
As polynomials. Like the way we did for Fibonacci.
Yeah.
So like Fibonacci is basically this.
I thought it's the other way around, like expressing polynomials in real world computation. Okay, it's expressing the computation in
Polynomials. Then you now use a protocol to check the polynomials. Do you get it?
Okay, this one is that triangle.
Yes. So Francis talked about, I was not here that time, but Francis talked about checking the number of triangles in a graph. That's a problem. That's a real world problem. But then he showed how to, I might have to go over it again at some point, but he showed how to go from that real world problem to polynomials. Then you now use sum check. Sum check is the protocol that can now check the constraint. So the constraint in that case is that the sum of, if you evaluate at the Boolean hypercube and you sum up all the evaluations, it's supposed to be a certain number. So the prover said, I've done that for you. I evaluated everything, I added it up, and I got 14. That's supposed to be the output. So sum check protocol is a protocol that can prove that a polynomial evaluated over the Boolean hypercube sums to a certain value. So the prover will now use the sum check protocol to prove that to you. But the process of converting from like the graph theory description to a polynomial you can run sum check on is arithmetization. Yeah. You get. So it's like problem, arithmetization, polynomial, protocol, proof. Does it make sense? What do you want to do now? Which break? Why are you taking a break? I think it's HC. Yes. So HC. So the entire field right now uses multilinear polynomials in a certain class, right? So there's like Starks and all those people, they use like univariate polynomials. There's now another branch, sum check based protocols. Those ones they use multilinear polynomials, right? We are more, I am more like sum check-ish. Francis is more stack-ish, maybe. I don't know. I might have changed. But like right now, this polynomials I've been using has been over like 0, 1. I don't think it's the right time yet. I think we need to talk about the graphical rep. Yes. Then show how you can bend those lines.
You said a bend.
It will be time for it.
Why actually the calculated sets were
Yeah. So I'll just introduce it.
high level.
No, right now it's like Rahima is not here. And she wants to show. Yeah. Multivariate. Yeah, I think all sum check based ones can use multivariate. Multivariate, sum check doesn't just force you to use multilinear. It allows you to use multivariate. So I feel graphical. Yeah. Okay. Then I want to hear the question.
Talking about graph theory,
Yeah.
I think our work is reduced them.
Why?
When I give a program to do something,
Yeah.
and the prover gives me, I want to be sure that the prover is correct in the work.
Yeah.
Me as a verifier, let's say you give me this Fibonacci sequence of function.
Mm-hmm.
I don't even have to do pick a point to check whether the person is correct.
You as a verifier.
Yes, tell the prover.
So evaluate the prover.
evaluate at the prover.
What will you do?
Talking about graph theory, maybe I've seen the pattern
Okay.
of this thing of the graph.
Mm-hmm.
If I can show that the graph is continuous, then the verifier is correct.
It's interesting.
Explain the meaning of that word.
Yeah. So that is exactly.
Continuity of a function is just talking about if I have a graph, any graph you can imagine, if I say that the function is, they define the function for me of that graph, I get it now.
Yeah.
If the graph is continuous, no matter the input I put there, it will always meet it. So I don't have to check at every point that.
As not continuous just means that there's no break in the graph, right?
There's no break in the graph, and that means every input of x will yield to a corresponding output.
Yes, that word no break.
Yes.
Okay. I don't know if that would. We'll have to explore it, but I don't know if that would be enough. Because right now it's just based on continuity, right? You're not taking into account the problem statement again, right?
So the problem statement is that I want to know whether the prover
Yes.
does the work.
Correctly. So like now in this example, what was this thing now? Here, right?
Yes.
So let's say they did it correctly.
Yes.
We're going to get a polynomial.
Yes.
Let's say he made a mistake here.
Yes.
We're going to get a different polynomial. So
From this, okay,
what
yeah.
I'm not asking, like, is there a way to detect
Where the problem
whether
is.
there's a mistake or no mistake? Like, if there's a way to detect it using the continuity thing, then maybe a protocol can be built out of that.
If I'm right, I'm not sure.
Yeah. What?
That again depends on it depends on like the value of each node. Like each node is like doing the same computation, and then the continuity thing is impossible. But if each node is doing the different computation, then there may be a problem. It may still be possible to do it, but
You're saying that you, like in this case now, right? These three, there's some relationship between them, right? And then these three, there's some relationship. And the relationship holds until the mistake.
Yes.
And something should
So at
be
that
detectable.
point, at that point that
There's a mistake.
there's a mistake, it will be discontinuous. They call something shift function. The thing will shift from that point to another point.
We'll explore it after class. Thanks.
I'm going to write our own paper.
I'm trying to wrap my mind around the entire thing, but I noticed that we started from a particular polynomial, FAB equals 2AB plus 3B, and then we went on to generate the, using that Boolean hypercube with 0,
Yeah, 0, 0, 0, 1.
0, 0, and then come up with this on the
Evaluation
right-hand side
point.
of it. And then what we just did next was just multiply by the Lagrange's.
Lagrange is the same.
And then when you resolve that, it just
Yeah.
gives you back what you had in the beginning.
Yeah. Yeah, like what's the point?
What's the point of
No, so the point is that you will not be given this usually.
Oh, okay.
So the same way, like, look at the Fibonacci. There's no polynomial. We don't know what the polynomial is. So we need to interpolate to get this f of x. Then we can now check things on this f of x. But polynomials have some property that if it's correct, then everywhere you check will be correct. But if it's incorrect, then most places will be incorrect. So there's a distinct way to know whether something was done correctly or not. So that's the point. We're looking for something that can detect that difference. So now what he's saying now is looking like, oh, maybe that might be able to detect such a difference. Once you have something that can detect difference, then you can make a protocol out of that.
So this is not I tried it. Whenever I put the value, which was maybe like 4, 5.
But when you put outside,
Yeah, it would. I was even getting decimals.
decimals. Are you using F?
Sorry, yeah. The negative numbers.
How can you get negative numbers in the field?
No.
What are you using F64?
Yeah.
Even though, right? I don't know actually. But yeah, maybe precision problems. We'll try it. I've never tried this before, but I just know that it should work.
I think they carried it.
Did it work?
Yes.
Yeah.
For any X? You use fields?
Sorry?
Use fields?
No. I'm trying to use field now. I use integral.
And it's just what?
We use fields now. You use FP
Oh, yeah. This guy didn't use random number.
Yeah. We'll check the code after. But even F64, I feel like it should work now. I feel like it should work. Well, we'll see. What else are we doing? Okay, design. Yes.
Yeah, so there's something I've noticed so far.
Yeah.
I don't know if it's correct though, but based on the implementations that we've made so far,
Yeah.
I noticed that in most of the things we've been doing in this entire ZK stuff, like our implementation, we have to do a lot with loops, and the main thing is, okay, knowing how to make use of loops and knowing what type of loop to use at every point in time.
Okay.
And what you're going to be doing inside each of the loop, because if we are talking about polynomials, you know, these are numbers, so we are always going to be doing something for each of those numbers. I don't know, so I just thought about it. And
So you're saying that if you invest in like loop.
No, not
Understanding
investing in
loop.
it, like, you know.
Understand? Wait, no. I'm like you invest in like understanding loops. Like you feel like you get a lot of reward in the future, right? Like
That's an observation.
Exactly.
Yeah, I'm not like investing in it. Like, okay, it's just like knowing when to do what and
Yeah.
how to do what.
Yeah.
That's it.
Yeah. Because you're most likely to be doing. I'll say too much, but yes, there's there are discoveries that you guys must make. Okay.
Wait,
Yeah.
it's okay. But I think like we've not talked about the quotient.
Mhm.
So when we talk about derivatives for hands,
Okay.
but people should just write it and run it.
The Fibonacci.
Yeah, the test.
At a random point. Like try it at a point outside actual quotient.
Okay. What do we do now? Can you guys do design? So how might you represent a multilinear polynomial in memory? Tuple or what? I mean, like, what does the tuple represent?
So it represents like if I have like maybe at index 0 basically.
Okay.
I can have like a vector or an array of tuples. And
Okay.
what each index represents is just basically a separate polynomial. So if I have like 2ab or a separate
Monomial.
yeah. So if I have 2ab plus 3bc, I basically have like the first index I have 1 1 because the degree of a is 1 and the degree of b is 1 as well.
Mm-hmm.
And then maybe I can have it can be 3 items in the tuple where I know the last is always going to be probably the coefficient,
Mm-hmm.
and anything before it just represents the degree of the various variables.
Mm-hmm.
If you get what I mean.
So, how will you represent this?
Okay,
2ab.
I can have something like 1 1 2.
Wait. So vec, right?
Yeah.
Okay.
A tuple with 1 1 2.
1, 1, 2. Uh-huh.
And then I can have one. Okay, sorry. There are 3 variables ABC. Okay, so it's going to be 1 1 0 2.
Uh-huh.
And I have 0 1 1 3.
Do you get this representation? So it has a value for each variable, right? So this is an f of a, comma b, comma c, right? So the 3 variable system. Now, if the variable's value is 1, that means that variable is on. But if the variable's value is 0, that means that's off. So 1 1 0 is saying that a is on, b is on, but there's no c. And the coefficient is 2. Do you get? So it's doing 2 a b. Then this one is a is not on, b is on, c is on.
It's just like sparse.
Yes. So it's 3 b c, right? So this is one potential representation of it. Does anybody have another rep? Yeah.
You can have like 2 tuples inside one.
Yeah, you can have 2 tuples inside one.
Like a tuple of the points.
A tuple of the variables
Yeah, variables.
and a tuple of, and the coefficient.
Coefficients.
So now he has adjusted this other implementation, right? So it's now like vec of, right? So like 1 1 0 and then 2. So this one I can access the coefficient quickly. And then 0 1 1 and then 3. Right? This is one another potential representation. Does anyone have another way to do this? So what kind of this pass, right?
Yes.
What would dense look like?
Maybe a dense.
Can you have dense? Oh yeah, that is possible. Can we have dense? You think it is?
20.
If you think we can have dance, let me wait. You think I have dance? Who else thinks we can have dance?
It's possible actually.
But this first one is looking like this.
No, this is pass, right? Because of it's directly mapping to the coefficient. Yeah, it's directly mapping to the coefficient. If you think dance cannot happen, let me see your hand. So if you don't know, let me see your hand. Kamal, you think it can happen? So, what is your suggestion? Wait, sorry. Multiple arrays? What will be inside the array?
The first one to probably now I'm talking about multivariate, not just maybe multilinear.
No, multilinear. Yeah. You don't know. Oh, why? What was the idea?
Because remember that what we were doing was based on implementing the exponents. That was the point of the
Dance.
Now, the thing that we're going to be changing mostly is going to be the coefficients. Maybe remove one variable, like this for now. Remove one
A, B, then B, C.
They're going to implement.
So you don't think dance can happen?
I don't think it's actually.
Okay. Where you are?
So yeah, I can't do one thing of how it happens because then we used to like map the index to the exponent. But now it's possible for one exponent to be 0 and the other exponent to be 1.
What do you mean?
So, like for A and B, like the exponent is 1.
Multilinear.
The exponent
It's always multilinear, right? So you will not have any A square. That's not what you're talking about, sorry.
Oh, okay.
You can never have A square. So this is never going to happen, right?
Yeah. So all of you that agree, I think we should do
So for evaluate the polynomial, so for instance, this 2
Yeah.
become a 2 2 2 0 plus 3 plus 0 3 3.
Wait. You said 2.
2 2 0 plus 0 3 3.
What's this?
I evaluated like since like 1 1 0. So 2 holding the constant and then the variable together.
Okay. Wait, how did you get 2 to 0?
So ABC 1 1 0 and then I multiplied through with 2.
Is this pass now?
No, I'm not. We're not doing just this thing now.
Is this pass? Do you know what sparse means?
Yeah, I know.
Sparse means that there's a direct correlation between, and that's all. Like when we had like the dance, right, for like x squared plus 2, right? We could have done this sparse, let's say just x squared plus x4, right? We could have done this sparse, which is just like, how did they do that again? Coefficient comma exponent, then coefficient comma exponent. So you can see it's mapping direct. But what was the dance? We now had to add things to the variable, right? So this x squared plus 4 plus x4 had to change into constant 0 plus 0x plus 1x squared plus 0x cubed plus 1x4, right? And then the representation was now 0 0 1 0 1. So it's more like we had representations for things that were not necessarily in the polynomial. But in this case now, you only have representations for things that are in the polynomial. So it's still sparse. Do you get? If the what?
Dance is possible.
Yes.
Then it will be the verb of I will since I have two monomials.
Yes.
So I will get the coefficient of the two monomials. For example, I will A separate, B separate, C separate.
Okay.
So I'll be getting tuple of 2 elements. because of the two monomials. So the first one, A, will be 2 comma 0, B will be 2 comma 3.
I don't get it yet.
So, okay, I have two monomials. I
Yes.
have three variables.
Yes.
Right? So I will have a tuple of 3 elements.
Okay. It's
This
sparse.
example is not. I have the third monomial now. I'll be able to do it. I have two monomials.
It's not
three
possible.
variables.
But the thing now is that, regardless of the polynomial, right, your representation is supposed to be able to handle that, right?
So I'm thinking about something, it's not complete yet.
Yeah.
So since this expression has just 3 variables,
Yes.
so in the first monomial, C is not there.
Yes.
So let's try to just put 1 on A, 1 on B.
Okay.
and
Power,
C,
right?
Yeah. Then C will be 0, then plus 3, A will be 0, B will be 1, C will be 1.
Okay.
So I'm still trying to think there might be a way we might factor out this. So it will be A, B, C, then 2 and 3 will be like in the matrix column. So
You want to do polynomial evaluation via matrix vector more?
So I feel like there might be a way to still simplify it.
Yeah. Continue searching.
So
Yeah.
it's possible to just say there are coefficients, then the individual power.
In power what?
That is the coefficients 2 with 1 1.
2, 1, 1.
2, then
That's
1,
sparse.
1.
That's sparse.
It's still translated to sparse.
Yeah.
No, I'm not putting like C now. I'm just.
Yeah.
Because if we add up the power, then if you now go to go back to invariant.
But your this representation will just have 2 things inside, right?
Yeah.
One for each monomial, right?
Yes.
That's sparse. Like it's just mapping straight away.
You said density, like you are basically specifying everything, right?
Maybe yes.
That means what we said at the beginning was basically density.
Yeah.
And it actually was
What does his question is like, what does specifying everything mean? What is that everything?
Oh, I see.
The way I look at this stuff is that I don't think it makes sense. You know, it could be give us this have representation of ABC where only A is 1. Have another representation where only B is 1. Another one where only C is 1. Then next one AB, BC, AC, then the third one. So that can be.
Yeah. So she has gotten how to do it. It inside doesn't make sense. Why would anybody do that?
Yeah.
We don't know. Well, let's continue. So what she's saying now is that you enumerate over all possible variable combinations, right? So you have 3 variables in your system, which is A, B, C, right? So this is what your dense representation will look like. You have the constant, still like almost like what you guys had in univariate, right? But then you now have A, B, C, then AB, AC, BC, then ABC. Then you just put the coefficient of the ones that are available, right? So this 2AB plus 3BC, there's no constant, right? Sorry, 2AB plus 3BC. So AB is 2 and BC is 3, right? Why the rest of them are 0? Huh? The constant is 0, no? Right? Right?
This is sparse.
This is dense.
Dense.
Yeah.
How was sparse?
Sparse? So sparse is the other one that we did.
But then why,
Yeah.
what is the arrangement?
Yeah.
Yeah, like the index.
AC can
now.
come before AB.
Yes. How do you
AB can-
choose?
So how do you know which?
You choose your own. You choose your own. But there are some that have like interesting properties. So when we were implementing, I implemented dense.
Or
Yes. So you said it doesn't make any sense. It does it actually. I had to change it to sparse at some point, but it's still dense-ish. This dense sparse. I did dense sparse. Why? Francis implemented sparse. You get?
So for univariate, dense is like
Dumb guy.
for like interpolation.
For what? Univariate. Univariate. It's dense or sparse now, right? Univariate doesn't. Like some people implemented sparse, some people implemented dense. There's no one size fits all.
But dense is preferable for univariate.
Why? Why? No, it's not. So for multilinear, there is a representation that is the best. Nobody has said that representation yet, or somebody has said it. I don't know, but there's a representation that is best for multilinear. Yes. I'm not. You guys have to figure it out for yourself now. But for univariate, it depends on the context, right? So FFT allows you to move between. No, actually, it doesn't matter. If I'm biased, if you force me, like gun to my head to pick one, I'll pick dense. For univariate. But it's not by force. Yeah, but efficiency and other things. Like FFT, for example, outputs. FFT can go from evaluation form to creation form, and to output it in dense. Maybe not, right? And you can write your FFT algorithm potentially to output sparse. You could. It's like there was more overhead.
So, but for this one now,
Yeah.
I would still like
Yeah, I mean, it's straightforward. That then so you have to start to prove all those zeros they confuse me.
So you're getting an idea for how you could potentially arrange them. If you can flesh that out, you will get exactly the implementation that I use. Dense, right? Yeah, maybe. But it's more interesting work. So,
Case in point. I said it has to be
yeah. Oh, okay. Yeah. To what? To what? FFT. Yes. Potentially. So this dense now, this pass. Now let's look at evaluation in both. Okay? So when you start looking at evaluation, you might have to say that, oh, if my representation was this way, I might be able to evaluate faster. Or is this way I might be able to do this. So let's now explore what's our current sparse. This is our current sparse rep, right?
Yeah.
We have a tuple for each variable. And then we have a tuple that contains each variable. And then we have the coefficient. Yeah.
So how did you get to 0?
No, sorry. This was you now. Was it you? Oh, okay. So it's a suggestion. But you get the sparse rep?
Yes.
You get the dense rep?
Yes.
Okay. So now how do you do evaluation for sparse? So now you're going to be given values for A, B, and C. Right? So how would you evaluate this rep? You say? What's exponent?
Passing.
And the one
Oh, you're calling those exponents of A, B, and C.
Yeah.
Okay. So let's say I'm giving A equals. Let's say I'm giving ABC, right? How would I evaluate this? I'll loop through. Okay, so now the first one.
First of then you do the second item.
That's 2.
That's two. And then now you're multiplying it. So you have to like maybe do a mapping through the or look through again through the tuple of exponents. And then for the first we know that the first
So that'll be 1, 1, right?
yeah
Uh huh.
is for the A, the second is for the B, and the third is for the C. So you just pick your A values. So A raised to
That's
the power
1.
that of
The exponents. So 1 raised to the power of 1.
Raised to the power that of 1, and then C raised to the power that of 3. Like index of 3.
So that's what I wrote down, right?
Yeah.
Then plus
Yes.
3.
Then you now do
Right?
So you have to move back to the first row. And then come down again.
So like a nested loop.
Yeah.
Right? This is what you're saying.
Yes.
So we do this, that's what? 2 times 1 times 2 times 1, right? Plus 3 times 1 times 2 times 3. So this is what? 4 plus.
16.
That's what?
22.
So we evaluated this at A is 1, B is 2. This is already 4, right?
Yeah.
Then 3 is what? 2, and C is what? 3, which is 18. And then we get it, so this 22. So that's one way to do it. Does it make sense what she talked about? So it's not like you're doing a dot product. Is it dot product? Yeah, you can also do a dot product. So you can also, rather than doing raised to the power, you can also do 1 times, 2 times, and 3 times. You get? Why it works is because it's multilinear. And you know that the power can never be more than 2. Yeah. So you can have it or you can't. So it makes sense, right? So this is one way. This is how you can do it. This is one way to do it with sparse. Multiply what by 1? What's everything?
Yeah, just like putting. Well, the ones that are not 0, you can just put in the exact value.
Yes.
Instead of being raised to the power.
But whenever you have an if statement, if you can do something without an if statement, it's preferred to do that thing without an if statement. Because of. Are you guys listening? If you can do something without an if statement, it's preferred to do it without an if statement. Because of when you have an if statement, there's a condition, right? And you can go one of 2 ways. Okay? So the computer cannot predict where you will go. So when it gets to that point, it will guess. It will guess where you will go. And then it will just follow one path. But when you now actually do the condition, if you now go the other way, it will now like it has done wasted work. And it has to now go and start again and try and get the other part. But if you don't have if statements, then the computer doesn't need to guess. It knows that 3 seconds into the future, you'll be here. So it will do whatever it wants to do. It might load some instructions earlier and stuff like that. So if you can do branchless programming, it's called branchless programming, where you get rid of branches. So there's something called branch prediction, branch misprediction. So if the computer is guessing wrongly, your program is slower. And if statements, anything. So in this case now, she was like, you can check if the tuple, if like the value is 1, then you just return the A, which you could do, but then it's not like so many guesses there and more chances of. So it's better to just do like the exponentiation or the dot product.
Can you explain that dot product again?
Okay, so now if you wanted to do this dot product, what you could do you know what dot product is? Okay, see, this is what dot product is.
Dot product.
Yeah. So you have 2 vectors, right? So let's say you have A, B, and you have something else, you have C, D, right? and you want to compute the dot product between them. What you do is that you will first of all multiply element wise, and then you add it all. So you multiply each element, so that's A times C, and then B times D. Then you add everything. So that will be A, C plus B, D. So what I was saying now is that in order to get the value, you can do the dot product between your ABC and the tuple. Okay? So let's say we wanted to do this one now, right? That will be 1, 2, 3 dot 1, 1, 0, right? So you do 1 times 1, 2 times 1, and 3 times 0. So that will be 1, 2, 0. Then you add everything together. That will be 2. Then you can just multiply that with your coefficients. Do you get 2 times 2 will be 4. And you can do the same thing for. Is that?
3.
That's true.
1 plus 2.
Are we wrong?
Oh, that's true. That's good.
Are we wrong? Yeah, we're wrong. Why is wrong? Because of, you see this, it's not adding them. It's multiplying them. So that product will not work there. Because this one now is doing exactly what those ones are doing, but the dot product is adding instead of multiplying. So that won't work in this case. So don't use dot product. Just forget what I said there. So you can just do, yeah, this works. This works. There are more efficient ways to do it though. You could use like an iterator and you could do like dot product or something to get that before thing. But does it make sense? Sparse. You missed what? How she? You get it you get the representation. Okay. So you get the representation. Now we want to evaluate this rep at A equals 1, B equals 2, and C equals 3. Okay? So you know that first one is the power of A, and the second one is the power of B, and the third one is the power of C. So what you just do is that you just multiply the coefficients by each of them raised to their respective powers. And at the end of the day, you get to this plus this sequences. You get that? So now, who can figure out how to do how to do evaluation for dense? So it's like nobody likes dense. Who likes dense?
I like
You like you like dense for univariate.
Yeah.
Who likes dense for multilinear? Nobody. Wow. Yeah. Okay. How will you know you don't have ABC?
No, like if you just have just 3 variables.
We have 3 variables.
Yes, we have 3 variables.
Yes.
So now, we said that how would you like the arrangements?
So yes, how will you choose an arrangement? You need to choose an arrangement, right? Because it cannot be random.
Yes, it can be.
Because technically, AB could have come before, could have come after AC. Even ABC could have just been anywhere. How do you choose how to order it? And what property? Yeah.
Since we have to make an ABC, you can actually use the kind of the other does not matter, right?
It might.
Doesn't matter.
Doesn't matter. I'm asking you
No,
too.
the thing is,
Sir,
you map,
can I
right?
see this class?
I mean, you
You
can
can
use
map.
I'm guessing what you're saying. Maybe we can spread up.
Wait, sorry. Do you want to copy this?
Yes.
Can you see it? Okay. Oh, yeah.
So like thinking of what you said,
Yeah.
like we're thinking of how to, the ordering, right?
Yeah. How do you choose
So
an ordering?
maybe we can, from aside the constant,
Yeah.
we can say the A is
Yeah.
0,
Uh-huh.
B is like 1,
Uh-huh.
C is 2.
Uh-huh.
So AB would
So if
be
you had
0,
D,
1.
what? If you had D, what would it be?
Eh? Here it would be 0,
Wait,
1,
wait.
2, 3.
If you had D, what would D be?
Eh?
3? Let's say you had A, B, C, D.
Yeah, D will be 3.
D would be 3. Okay.
So AB will be 0, 1.
Uh-huh.
AC will be 0, 2.
Uh-huh.
AD in that case will be 0.
Okay, go back to ABC.
Okay, so
So you're giving everyone a number or something?
yes.
Let me help. Have you copied it? So you're saying this is 0, right?
Yes.
Then this is 1.
1.
Then this is 2.
Yeah.
Then this is now what?
0, 1.
Uh-huh.
0, 2. Then B will be like that.
So what do you use this for?
Uh-huh.
Or what number is this?
Wow.
So continue. You just yeah.
I said another
Yes, exactly. No, that's not.
Okay.
So what I'm thinking about is, first of all, when we look at the representation, we see that there are 7 elements inside. Once we see that there are 7 elements, then we already know that, okay, the representation in a Boolean hypercube will give you 2 raised to the power of n minus 1. I don't know. So if maybe we are having like
it's 8 elements.
Let's check for 2 variables and see if that stuff holds. So if it's for 2 variables.
So you want to map them to the Boolean hypercube?
So what I'm trying to do is, let's know what to the number of elements to expect in the array. So if we know that, okay, this
1, 2, 3,
for now this vector has
8 elements.
No, from I think from the number of elements in the array we can know the number of variables.
Yes.
So now if we do 2 raised to the power of
something.
2 raised to the power of something
Yeah.
minus, because normally if we do 2 raised to the power of 3 it gives us 8.
8, yes.
You understand? But we have 7 here.
No, we have 8.
8.
Yeah, you didn't
So
count
if we do 2
constant.
raised to the power of 3 gives us 8.
Yeah.
So automatically we know that it's 3 variables. If
Yes.
we do 2 raised to the power of 2, it gives us 4.
Yeah.
That means if we have 4 members, 4 elements in the array, we know that it's 2 variables.
Yes.
Just power 6.
Yes, exactly. So, okay, now you know that you know the number of variables, right? You know it's going to be what? 3.
Yeah.
So what do you do with it? Or how does that help you arrange your
It's just, see, sorry, mathematics. If I have 3 elements, and the
alphabetical order? Is that what you want to say?
3 elements,
ABC.
alphabetical or not alphabetical, I can always get the
Power set.
the power set of that element.
Yes.
Then
So how do you arrange the power set?
then I will index it.
By index, what will be the index? Like what's the index of AB? Or what's the index of
No,
AC?
the point is that I'm the one implementing, right?
Yeah, so you choose your...
Yes, I will choose my...
How will you choose your own?
You know I'm not good.
So we can apply it here. So we can either the same way you arranged it.
Yeah.
So we can go with the first guy is going to be the constant. So it's going to be the constant. The second guy is going to be the first variable.
So are you doing alphabetical?
Yeah, alphabetical.
You are doing it based on A, B, C, right?
Yes.
So constant, right?
Yes.
Then you do the first one. Is this what's this? This was food. Oh. A, right?
Yes.
B.
Yes.
C.
Yes.
So what will be the next one?
A, B.
So you go first, second.
Yeah, first,
okay.
second.
Then are you going first, third?
Yes.
So AC, right?
Yes.
Then what next? BC.
BC.
Then ABC.
Yes.
Okay. So this is one representation, right?
Yes.
And it will be consistent. Like
Yes.
you always give it like this.
Yes.
Okay. Is it good for evaluation though? Let's see. So now, what if you want to evaluate?
How would you know that this is
Exactly.
I don't know. You can.
So if we want to evaluate,
Yeah.
I think we can still use what she did in the first guy. So let's say we are giving
ABC.
ABC.
So I'm removing this one, right? Because exactly the same thing as the one on top, right? This is your ordering. The one I wrote on top is the same thing.
Leave the ordering now.
No, it's the same. It's the same ordering. So now I'm giving you concrete values so that I can test out what you want to propose for evaluation now.
Yes.
So this is representation of 2AB plus 3BC. in your dense ordering?
That's gone up.
The best way, I guess,
Okay.
is to represent everything in a Boolean type.
That's what you want to say too.
Yes.
Oh yeah.
Then
Then what?
your coefficient will automatically zero.
You don't care about that one,
Then when your coefficient is 2, your
That's
A-
0, 1, 0. Okay, this one. Okay, let me now put the Boolean hypercube on it, right? 0, 0, 0, right? Okay, so 2 now is 1, 0, 0.
No, now
No, 2 is 1, 1, 0.
But the Boolean hypercube is.
Another bit, if you want to say Boolean hypercube, I think the best way you should do it is that you should have half.
Half what?
Yes, first of the zeros, then ones, then the second.
So tell me what to do. How will I represent the zeros first?
Okay, zeros, 4 zeros. If they have like 3 power 8, 3 power 3, 3 power 3. Half it. Represent the first half with 0, second half 1. Then the next bit, half them again, 0, 0,
So
1, 1.
now you are saying that this ordering of the Boolean hypercube is not what you want. You want a different ordering.
To be easier, I guess.
Will we get exactly the same
Because
ordering?
when you put it this way,
Wait. I don't even understand the ordering proposition, right? So I'm trying to understand that. So are you proposing a different? So what you're proposing, will it be different from this?
okay.
If it's going to be different, let me clean it and then we'll try and write it out how you are
Now,
saying
know
it.
that this ordering is wrong.
For
The reason it's wrong is that we are trying to represent A,
okay.
B, C. A is
So you
present.
want a, so it's more like the sparse, right? If it's present, you want 1.
If it's okay, yeah. If it's present,
You want
if
1.
A is present, the first term will be this A will be 0. No, 1, 0, 0.
Which term? This one.
No, A on top.
Yeah, which is A, yeah.
Yes.
Okay, I get your repetition now. Okay, let me write your rep. That's basically the sparse rep, the tuple. So this one is 0, 0, 0, right?
Yeah, okay.
Then this one is 1, 0, 0. Then this one is 0, 1, 0. Then this one is 0, 0, 1. Then this one is 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1. Right? Okay.
Well, I don't get
What if we just make it like zeros, like you should make it like go the way it was before. But then just the letters will just be the one that are not ordered according to like alphabetical order.
I get what you mean too.
It should be
So you're
zero.
saying that you can still use 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. But then this will be const. Then this will be C. Then this will be B. Then this will be what? No, it's not A again, it's BC.
I just went to your code and you did this.
Exactly.
Wait, why is A in the middle?
Now,
Why is A
Your phone,
here?
you did this.
So it will be easy like that.
Okay. So let's see now. So when we have this now, this 2AB plus 3BC will be different, right? So 2AB, where's AB? Where's BC? Right? Then the rest of them are zeros. So they has changed the dense representation now to a new form. So then now we have this. How do I evaluate this?
now that you know that you're evaluating like over a Boolean group, you are starting 0, 0, 0, 0, 0. So you can now move through and say like, okay, let's say like, okay.
You can easily add them when you do for
You just do the calculation you did before.
when you do for death. When you do for death in the other one, so we contain the evaluation for the first monomial, which is 0, second monomial 0, the third one 0.
I get what you guys are saying. I guess you know. Okay. So yeah, iterating over. What you said?
You add them together.
I know that. Yeah, it makes sense. It makes sense. Yeah, yeah, yeah. So you guys have somehow converted it to something similar to the other sparse by rearrangement. So what they are saying now is the same thing they did here. That means you need something that can iterate over the Boolean hypercube,
Yes.
right? Right?
Yes.
Right? So I'm guessing you can have something that iterates over the Boolean hypercube, then you can zip it with this guy. So it's not like sparse-ish.
So this is the dense part of it.
It's something like that. That's fine.
Yes, now.
No, it's dense, yeah, but yeah. You get. So then you now use these ones as the powers or as the multiplicants. Are you confused with your own proposition?
No.
So like this three now, right? 30011, right? And then you're trying to evaluate at what? 1, 2, 3, right? So if you have something that could generate the Boolean hypercube, there's no reason why you won't know that 3 is like 0, 1, 1, right? So what you now want to do is you basically take this and raise it to the powers, like you just drop it down, right? So that will give you like 1, 2, 3, right? Then you multiply it. That will be what? 6. And 6 times.
Then that means you have to be able to tell the system to evaluate, to draw out the alphabet according to these numbers.
What alphabet? The Boolean hypercube?
Like
The zero,
in a 3 variable system.
yes.
The
To
system
generate.
has to recognize that A is O1, B is O1, O.
So the way they arranged it, it doesn't even care anymore. Okay, yes, but yes. Yes. So the arrangement is hard, right? The arrangement is hard.
Because that is system.
Yes.
Why?
Why? You will get there and get stuck.
The food is not interesting.
Where did you start?
Just like stress.
No. I'm sure they are not doing it. They have to see the possibility. Yeah, they have to see that it's possible.
Let's guide the team. Come like.
So let's do this one, right? 1, 1, 0, right? So 1, 2, 3, right? Raise to the power of 1, raise to the power of 1, raise to the power of 0, right? So that's what? 1 times 2 times. So it's still recording. Okay.
This OBS. You don't close. It's OBS.
So you didn't die, I just saw it even offside. He slept, he didn't die.
Go and use Mark, is a lie.
What? Come my lesson and we laptop you. He slept, he didn't die. You have to say about now what if you that we have
It's past. We don't have another array. But you are talking about a different. So that's like sparse on steroids now, right? Coefficients and tuple powers. Then for every possible. You're talking about this, right? Yeah.
It's not better to just
Like an array.
But it's still the same thing now. Like, yeah, just holding. This is what you mean, right? This is what you mean? Okay, what do you mean?
I mean, it starts with a new, like, let's start with. Why do you use the Boolean hypercube? Let's put an array inside.
So now, since we have an array, then we can put the coefficient there.
Okay,
Then
if
comma,
it's A,
any
if
other
it's
like,
B.
thing we are trying to put is like the power.
And that's fast.
Like this. But for everything.
So for everything.
That's
So
fast.
you are doing sparse, but you expanded it.
Somebody already
So it's like it can work, but it feels strictly worse. Strictly worse just means that it does not feel like it's better than let's say the sparse in any case. You get, because it's just like sparse, but you left some. Yeah. So this is 2, right? Then 2 times 2 is 4, right? Which is 18 plus 4, which is equal to 22. So it works, right? This works. This can give you. I feel like they will now have. Okay. Yeah, let me introduce something to you. Sorry. There's something called partial evaluation.
I said
So you know now we have multiple variables, right? So A, B, C. There's no reason why we need to evaluate all of them at once. We can evaluate A only. We'll now be left with something that is just B, C. Or we can evaluate A, B. So now, in your representations, how will you do partial evaluation? Do you get what I mean? Let me now do. So this is 2AB plus 3BC, right? Yeah, we could. So let's say we have B. We only want to evaluate B at 2. That's the goal. Right? So this is now going to be what? 2A times 2 plus 3 2C. This is now what? 4A plus 3 plus 6C. 6C. So what we're saying now is that, first of all, you represent this using your rep, right? So you could have used like sparse, right? Which is what? Let's say 2, 1, 1, 0, right? And then you can also do 3, 0, 1, 1, right? This is the representation of the inputs. Then you now call partial evaluation with B equals 2. So what are you going to get? You're going to get 4, 1. So now 0, 0, right? And then 6, 0, 0, 1. So you need an algorithm that can take you from that to this.
I think we need to start together, then we can take us to
What is better?
Like, start.
I saw the solution that you tried.
So it's like just kind of some chores.
Yes, now. You used to be thrown into the deep end. I'm here to. I'm the lifeguard. Don't worry. You won't drown. You won't drown. Oh my. Wait, is this thing recording? This is not moving now. Yeah, but see the screen. It's showing. It's showing the iPad. Even though behind it, it's supposed to be showing the terminal. So there's something wrong. I'll stop it.